Hello there and welcome to Science for Sleep, the little corner of the internet where science slows down, where curiosity stretches out like a warm blanket, and where we take our time with ideas that are usually presented too quickly to really sink in. This space is not about rushing or overwhelming the mind with facts, but about letting knowledge unfold gently, the way a conversation might drift late at night when the world is quieter. Tonight, we'll be wandering into one of the most astonishing possibilities that modern science has put forward. The idea that our entire universe, all of space and time, and everything within it, may actually exist inside a black hole. It sounds dramatic, it sounds impossible even, but the scientists who study such things have found reasons to take this idea seriously. Not because it's a wild piece of science fiction, though it certainly feels like one, but because when we follow the equations and the evidence as far as they'll go, this strange picture of reality begins to take shape. Before we sink into the details, I wonder where you are right now as you listen. Are you curled up in bed, maybe with a dim lamp glowing nearby, or are you stretched out on a couch letting the day slowly fade? What's the time on the clock where you are, and what does the night or morning look like outside your window? These questions may seem simple, but they're also deeply tied to the mystery we're about to explore. Because if scientists are right and we do live inside a black hole, then even the ordinary clock on your wall, even the rising and setting of the sun, would be part of the interior of this colossal cosmic object. Every moment of your life would be happening within its invisible boundaries. If you find this quiet journey interesting, if the ideas we unravel together give you a sense of calm wonder, or simply help you relax into sleep, I'd be grateful if you left a like or subscribe to this channel. It's a small gesture, but it helps more people discover this space where we can talk about the strangest corners of science without hurry. And now, with that invitation gently placed, let's begin to step into the question of black holes, and how they may not only exist out there in space, but may be the very stage on which our universe plays out. Black holes have a reputation for being frightening. The name alone suggests darkness and destruction, a place where light itself is trapped and nothing can escape. And yet, if we set aside the drama and approach them with patience, they reveal themselves to be far more fascinating than terrifying. A black hole is not a monster roaming space, not a vacuum cleaner sucking up everything nearby. Instead, it's an inevitable consequence of gravity taken to its extreme. When a massive star burns through all of its fuel, when it can no longer resist its own pull inward, it collapses. The collapse doesn't stop at a new balance point the way a smaller star might. It continues until matter is compressed beyond what our physics can fully describe. What's left behind is a region of space where gravity is so strong that not even light, the fastest thing we know, can break free. For a long time, black holes were thought of as curiosities in the math, strange solutions to Einstein's equations that probably had no real counterparts in nature. Even Einstein himself doubted they existed. But over the past century, evidence has piled up until there's no room left for doubt. Astronomers have observed stars orbiting invisible objects, moving so quickly and so tightly that only a black hole could explain their paths. They've seen the glow of hot gas swirling just outside the boundary of one, emitting powerful X-rays before disappearing forever. And in recent years, we've even managed to capture an image of the shadow of a black hole itself, outlined against a glowing ring of matter as it fell inward. These are not abstract concepts anymore. They are real as the earth beneath your feet. The part that begins to touch our story tonight is that when you study black holes carefully, when you follow their strange properties to their logical conclusion, they begin to resemble something familiar on a much larger scale. A black hole, with its mysterious boundary and its interior space, looks uncannily like a miniature universe. And that's where the idea comes in, the possibility that our entire cosmos might not just resemble a black hole, but actually be one. At first glance, this sounds absurd. We look up at the night sky and see billions of galaxies, each containing billions of stars spread across unimaginable distances. To say that all of this is somehow inside a black hole feels like a trick. But remember, we don't see the outside of our universe. We only see what's within it. If the universe as a whole were sitting inside the event horizon of a massive black hole, there would be no way for us to look beyond it. Everything we observe, every galaxy, every particle, every ray of light would be contained within its boundaries, and that means the possibility, as outlandish as it sounds, can't be dismissed outright. The story begins with the concept of the event horizon, the boundary around a black hole. This is the point of no return. Once something crosses it, whether a spaceship, a star, or a beam of light, it cannot escape. From the outside, the event horizon looks like a dark sphere, a place beyond which information disappears. But from the inside, the story is stranger. To an observer falling in, nothing special marks the crossing. They pass through the horizon as if it were empty space, and only later, as they approach the singularity at the centre, do the forces become overwhelming. This is one of the oddities of relativity. What looks like a hard barrier from the outside can feel invisible from within. Now imagine for a moment that our universe has an event horizon of its own. Not in the sense that we're all about to be pulled into oblivion, but in the sense that there is a limit beyond which we cannot see. Astronomers already know such a limit exists. It's called the cosmic horizon, the boundary beyond which light hasn't had enough time since the Big Bang to reach us. From our perspective, the universe ends there, not because there's nothing beyond it, but because it lies outside our observable region. If you place these two ideas side by side, the resemblance between a black hole's event horizon and the universe's cosmic horizon becomes impossible to ignore. Scientists who have followed this line of thought have discovered even more parallels. The way space expands inside our universe, the way time flows differently near the edge, the way the distribution of matter behaves, all of it maps onto the mathematics of black holes. Some theorists suggest that the Big Bang itself, the moment when our universe began, might be the mirror image of what happens when a massive star collapses. Instead of everything falling inward, from our perspective inside, everything expanded outward. What looks like a collapse from outside might look like a creation from within. This is a lot to take in, and it may sound like we're venturing too far into speculation. But that's the beauty of exploring these ideas slowly and carefully. We don't need to rush to conclusions. We can sit with the strangeness and let it unfold, the way a story does when told around a quiet fire. Step by step, the pieces come together. Black holes are not just destructive, they're also creative. They may not only swallow matter, but may also give rise to new regions of space-time, bubbles of reality sealed off from the parent universe. If that is true, then our universe might simply be one of many. A child of some larger cosmos, a black hole born in another reality. From this perspective, when we look at the stars, we're not just looking outward, but also inward, deep into the interior of a black hole. The thought may feel unsettling, but it is also profoundly unifying. It suggests that the same laws that govern the fall of matter into a collapsed star could also govern the vast sweep of galaxies across the heavens. The very forces that seem to confine may also be the ones that create. And this is just the beginning. To truly appreciate why scientists take this possibility seriously, we'll need to explore the nature of space and time, the role of Einstein's theories, the evidence of cosmic expansion, and the curious way black holes connect to thermodynamics and quantum theory. Each of these pieces adds depth to the picture, showing us not just that the universe could be inside a black hole, but also what that would mean for our understanding of reality itself. So, take a slow breath. Let the idea rest for a moment, and know that we are only starting our journey. Ahead lies gravity's pull, horizons we cannot cross, singularities hidden at the centre of things, and the suggestion that reality is far stranger than it first appears. Black holes are among the strangest predictions of physics, and they carry a mystery that has kept scientists fascinated for more than a century. When most people first hear the phrase, they imagine a kind of cosmic monster, a bottomless pit in space sucking up everything around it. It sounds like something out of a science fiction movie, and for many years that was exactly how they were treated, as mathematical oddities too extreme to actually exist. Even Albert Einstein, whose equations of general relativity first hinted at them, believed that nature would find a way to prevent their formation. Yet the more carefully scientists studied the sky, the more evidence appeared. Until today, the existence of black holes is no longer in doubt. What remains uncertain is exactly what they are, and how deep their mysteries go. To understand the strange qualities of black holes, it helps to begin with gravity, the familiar force that keeps our feet on the ground and the planets moving around the sun. Gravity is everywhere, and yet it is the weakest of all the known forces of nature. You can test this with a simple magnet. A small refrigerator magnet has no trouble lifting a paperclip off the ground, even though the entire Earth is pulling on it at the same time. For gravity to truly dominate, you need a lot of mass gathered in one place, like a star. Stars exist in balance between gravity pulling everything inward and nuclear fusion in their cores pushing outward. As long as that balance holds, the star shines steadily. But when the fuel is exhausted, gravity takes over, and the result depends on the size of the star. Small stars become white dwarfs, medium stars become neutron stars, but the most massive stars collapse beyond all limits, forming black holes. It is in that collapse where the real mystery begins. As matter falls inward, there is no known force that can resist it. Protons, neutrons, even the very fabric of atoms are crushed together. According to general relativity, the collapse continues until all of the mass is concentrated in a single point of infinite density, called a singularity. Around this point forms the event horizon, the surface beyond which nothing can escape. Already we can see why black holes are mysterious. A singularity is not something physics can describe. Our equations break down, and the usual rules of space and time no longer apply. It's like reaching the edge of a map and finding no more paper to draw on. What makes this stranger still is that the event horizon behaves in ways that challenge our intuition. If you watched an object fall toward a black hole, you would never see it cross the horizon. Instead, time for that object would appear to slow down, creeping ever more sluggishly as it approached. From your perspective, it would freeze in place, fading away as the light it emitted grew weaker and redder. From its own perspective, though, the object would fall right through, crossing the horizon without noticing anything unusual, until eventually being pulled to the singularity. This contradiction is not a trick, but a reflection of how relativity works. Time and space are not absolute. They depend on where you are and how you move, and black holes stretch that relativity to its limits. Astronomers have found black holes in many different sizes. The smallest are formed from collapsing stars and may contain a few times the mass of our Sun. The largest are called supermassive black holes, with masses equivalent to millions or even billions of suns. These giants sit at the centres of galaxies, including our own Milky Way, where one called Sagittarius A star hides behind clouds of dust and stars, revealed only by the rapid orbits of nearby stars and the faint radio signals we can detect. We now know that nearly every galaxy harbours such a monster at its core, and their influence helps shape the evolution of galaxies themselves. But even knowing all this, black holes remain full of puzzles. One of the most famous involves information. In the 1970s, physicist Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon allow them to emit a faint radiation, now called Hawking radiation. Over immense timescales, this would cause a black hole to shrink and eventually evaporate. But here lies the paradox. If the black hole disappears, what happens to the information about everything that ever fell inside? According to the laws of quantum mechanics, information cannot simply vanish. Yet from the perspective of relativity, once something crosses the horizon, it is gone forever. This conflict between two of the most successful theories in science has not yet been resolved, and it stands as one of the greatest unsolved mysteries in physics. Another puzzle is the possibility that black holes are not the end of the story at all, but doorways to something else. Some scientists have suggested that the singularity at the heart of a black hole may not be a final point of destruction, but the beginning of a new region of space-time. From this perspective, what we call a black hole might be the seed of a new universe, expanding on the other side of the singularity. To us, everything appears to fall inward, but from the inside of that new universe, everything appears to expand outward, much like the way we see our own cosmos expanding since the Big Bang. This is where the idea that we ourselves might live inside a black hole begins to take shape. The similarities are striking. A black hole has an event horizon that separates its inside from the outside world. Our universe has a cosmic horizon, a boundary beyond which we cannot see. A black hole has a singularity where space-time begins or ends. Our universe seems to have begun in a singularity of its own at the Big Bang. The mathematics describing each have uncanny parallels, suggesting that they may not just resemble one another by coincidence, but may actually be the same kind of thing viewed from different perspectives. The mystery deepens when we look at the behaviour of time near a black hole. Time slows as you approach the horizon, and at the singularity, time as we understand it ceases to have meaning. Inside our universe, time also behaves strangely. Near the Big Bang, time itself seems to emerge out of the initial conditions, and at great distances near the cosmic horizon, time stretches differently than it does here on Earth. These echoes between the behaviour of time in black holes and the behaviour of time in the cosmos give scientists reason to believe the connection is more than superficial. And then there is the question of entropy, the measure of disorder in a system. Black holes have entropy proportional to the area of their horizons, not their volume. This was a surprising discovery, but it ties directly into ideas about the fundamental nature of the universe. Our cosmos too appears to have entropy related to the area of its boundary, leading some to propose that the universe itself might be holographic, its three-dimensional reality encoded on a two-dimensional surface, much like the horizon of a black hole. These ideas are still under debate, but they strengthen the sense that black holes are not isolated curiosities, but central to understanding reality itself. For all of their strangeness, black holes have become part of our everyday picture of the universe. We see them powering quasars, the brightest objects in the sky, fueled by matter falling into supermassive black holes. We see their influence in the merging signals detected by gravitational wave observatories, ripples in space-time created when two black holes spiral together. Each of these discoveries confirms that black holes are not just theoretical, they are active players in the cosmos, shaping galaxies, releasing energy, and bending the very fabric of space. Yet even with all we know, we are left with more questions than answers. What exactly happens at the singularity? Does information escape through some unknown process, or does it remain trapped forever? Are black holes connected to other universes, and if so, could ours be one of them? And perhaps most intriguing of all, are black holes telling us that our picture of reality is incomplete, that we need a deeper theory beyond relativity and quantum mechanics to understand what is truly happening? The mystery of black holes is not just about distant objects in space, it is about the limits of our understanding. Every time we think we have pinned down the laws of nature, black holes remind us that those laws may not be the final word. They are like cracks in the surface of a painting, hinting at a deeper layer beneath, one we cannot yet see. And that is why scientists keep studying them, why they keep building more powerful telescopes and detectors, why they keep running calculations and testing ideas. Because in the mystery of black holes may lie the key to the mystery of everything. When scientists say that our universe might exist inside a black hole, the first reaction most people have is disbelief. It sounds too far-fetched, too fantastical, as if someone took a plot from science fiction and dressed it up in physics. But what does it actually mean to live inside one? To make sense of this idea, we need to step carefully through the layers of meaning, because it is not about being crushed or pulled apart, And it is not about the end of the world lurking just beyond our reach. It is about the structure of the universe itself, and the strange way reality may be nested inside larger realities. Living inside a black hole would not feel any different than living in any other kind of universe. That's the first thing to understand. When astronomers point their telescopes at galaxies billions of light years away, they are not peering towards some outer wall of the cosmos. They are looking across space that stretches smoothly in every direction. From the inside, a black hole does not look like a hole at all. It looks like a region of space expanding in every direction. That's why the idea is so compelling. It fits with what we already see. Our universe is expanding, galaxies are drifting apart, and the farther away they are, the faster they recede. This is precisely the kind of behaviour that might be expected if we're looking at the inside of a black hole, where space itself is growing as it stretches toward the future. One of the key reasons scientists entertain this possibility is because of what relativity allows. Einstein's equations do not forbid new regions of space from forming inside the collapse of a massive object. When a star collapses to form a black hole, from the outside it appears as if everything is compressed into a singularity. But from the inside there may be an entirely new expanse of space-time hidden behind the event horizon. That expanse could evolve much like our universe has, with its own beginning, its own expansion, and its own history. If that's the case, then what it means for us to live inside a black hole is that the Big Bang itself may have been the moment of formation, the branching off of our universe from a parent reality. For many, this picture raises questions about everyday life. If we are inside a black hole, why don't we see the edges? Why don't we feel the pull toward the centre? The answer lies in perspective. From the inside, there are no edges to see. The event horizon is not a boundary you can approach, touch, or mark on a map. It is the limit of what can be seen, the edge of the observable universe. Beyond that, light has not had time to reach us since the beginning, just as light cannot escape from within a black hole to reach the outside. In both cases, there is an unseen barrier, not because something solid blocks the way, but because the structure of space-time itself prevents information from crossing. To live inside such a structure is to live in a place where everything you know, every star and planet and particle, is part of the interior of a cosmic object. The walls of that object are unimaginably far away, so far that they can never be reached or crossed. For practical purposes, it feels infinite, and for all intents and purposes, it is infinite to us. You will never reach the horizon of the universe, just as you would never notice crossing the horizon of a black hole from within. The physics ensures that your experience of life, of movement, of time, continues smoothly, without any break. That's why the idea doesn't immediately clash with observation. It is perfectly consistent with what we see. Another way to think about this is to imagine nesting dolls, the kind that fit one inside the other. Our universe, in this analogy, would be one of the smaller dolls, nested inside the larger one of a parent cosmos. That larger cosmos may have its own stars, galaxies, and perhaps its own civilizations, though to us they are unreachable. The black hole in that parent cosmos would have collapsed, and inside it, a new reality blossomed, which is ours. The dolls go on, possibly infinitely, universes within black holes within universes, a structure without a clear beginning or end. This picture changes the way we think about the Big Bang. Traditionally, we imagine the Big Bang as the absolute beginning, a moment when time and space came into existence out of nothing. But if our universe is the interior of a black hole, then the Big Bang was not the ultimate beginning. It was a transition, the birth of one region of space from the collapse of another. The singularity that seemed like an endpoint from the outside became a new beginning from the inside. This makes the concept of living inside a black hole less of a strange fantasy and more of a serious contender for explaining where we came from. Of course, there are consequences for how time behaves in such a picture. Inside a black hole, time flows differently than it does outside. The stronger the gravity, the slower the passage of time. Near the singularity, time as we know it comes to a stop. But inside a universe created by such a collapse, time would emerge in a fresh way, flowing forward as space expands. That forward flow is what we experience as the arrow of time, the sense that the past is behind us and the future ahead. Living inside a black hole would mean that this arrow of time is itself tied to the geometry of space, shaped by the fact that we are inside a bounded structure. It also means that space itself has a curvature set by the conditions of that collapse. In our universe, we see evidence that space is nearly flat, stretching outward with only the gentlest curve. That tells scientists something about the size of the black hole we may be inside, and the way its horizon defines our cosmic scale. If we are inside, the black hole that birthed us must have been unimaginably large, with mass beyond anything we can directly comprehend. The thought is staggering, but it matches the immensity we see when we look into the sky. What it means for us, practically, is not that danger surrounds us, or that collapse is imminent. To live inside a black hole in this sense is to live in a universe like any other. The stars will continue to burn, the planets will continue to orbit, and life will continue to unfold without any special peril. The black hole we are in is not something waiting to swallow us. It is the structure that makes our cosmos possible in the first place. We are not at risk because of it. We are here because of it. Thinking this way also changes the way we view the relationship between universes. If each black hole has the potential to seed a new universe, then every collapse is also a creation. Every time a massive star dies and forms a black hole, it may be planting the seed of another reality. That reality would be inaccessible to us, sealed off behind the event horizon, but from the inside it might look as vast and rich as our own. And that brings us to a startling realization. We may not just live inside a black hole, but the very existence of black holes in our cosmos may mean that countless other universes exist as well. This brings with it a subtle shift in perspective. The cosmos we see may be just one among many, each with its own laws, its own constants, its own possibilities. In some of these, stars may form and life may flourish. In others, conditions may be too different for anything familiar to arise. But if black holes are indeed gateways to new universes, then creation is not a single event, but an ongoing process, repeating endlessly, with universes budding from one another like branches from a tree. For us, living inside one of these black holes simply means that our reality is one such branch. We are part of a cycle of collapse and creation that stretches beyond what we can measure. It doesn't change how we wake up in the morning, or how the seasons turn, but it does change the context of everything we know. The ground beneath our feet, the stars overhead, the flow of time itself, all of it may be the interior of a black hole's space-time. And to think of it that way is to step into a wider view of existence, one in which our universe is not isolated, but one among countless others. This idea remains a hypothesis, not a proven fact. But what makes it worth exploring is that it arises naturally from what we already know. Relativity predicts the existence of black holes. Observations confirm them. The parallels between their properties and those of our universe are striking. To live inside, one may simply be the most natural interpretation of the evidence. And if that is the case, then our everyday reality is already far stranger and more fascinating than we ever imagined. When people hear the phrase fabric of space, it often sounds like a metaphor, as if space were a kind of invisible cloth stretched across the cosmos. But to scientists, it is more than a metaphor. It is a way of describing how the universe itself is structured. Einstein's theory of general relativity, which has guided our understanding of gravity for over a century, tells us that space and time are not separate entities, not a stage on which events unfold independently of one another. They are woven together into a single four-dimensional continuum known as space-time. It is this fabric that curves and flexes under the influence of matter and energy, and it is this fabric that gives rise to the force we experience as gravity. Imagine placing a heavy ball on a stretched sheet of rubber. The sheet bends downward under the ball, and if you roll a smaller ball nearby, it curves inward along the slope, That is the image often used to explain relativity. But the truth is deeper than that. The universe is not a flat sheet in a larger space. The curvature is not in a direction we can point to. Instead, the bending is intrinsic to the fabric itself. Time slows near massive objects, space contracts, and the paths of light and matter bend. Not because of some invisible force pulling them, but because the very geometry of reality is curved. This way of thinking about space is crucial to the idea that our universe might be inside a black hole, because what defines a black hole is not a physical surface or a tangible wall, but a region of curved space-time. The event horizon is simply a boundary where the curvature is so extreme that paths of light all point inward. Inside that horizon, the very meaning of direction changes. What looks like moving forward in space is, in fact, moving inevitably toward the singularity. And when you step back and think about it, our own cosmos has something very similar. On the larger scales, galaxies move apart not because they are travelling through space, but because space itself is expanding. The fabric is stretching, and everything embedded in it moves with the stretch. This expansion is one of the most striking features of our universe. Astronomers discovered it in the early 20th century when they noticed that distant galaxies are all redshifted. Their light stretched to longer wavelengths. The farther away a galaxy is, the faster it appears to be receding. This is not motion in the ordinary sense. It is space itself carrying the galaxies apart, and when you compare this with the interior of a black hole, the resemblance is uncanny. Both involve curved space-time, both involve horizons beyond which information cannot reach, and both involve regions defined not by physical edges, but by geometry itself. Living within such a fabric means that everything we know is shaped by it. Time flows differently depending on where you are. Gravity is not a pull, but a bending. Even the speed of light, which is the ultimate limit, is not just a property of photons, but a reflection of how space-time is structured. When scientists say we might live inside a black hole, what they are really saying is that our entire stage of existence, the fabric of space and the rhythm of time, may itself be part of such a curved region. The cosmic stage we inhabit would not be free-floating, but nested inside a larger structure, defined by the geometry of a black hole's interior. To understand how this would feel, imagine an ant crawling across a balloon. The ant has no concept of the balloon as a whole. To the ant, the surface simply stretches in all directions, seemingly endless. Yet from the outside, the balloon is finite, curved, and contained. That is our situation. From within, space feels infinite. Galaxies stretch beyond the reach of our telescopes. There are no visible boundaries. But from a higher perspective, one we cannot access, the entire structure might be enclosed, finite, and contained within the event horizon of a black hole. The cosmic stage is not static. It is dynamic, restless, always changing. The universe has been expanding since the Big Bang, and it continues to expand today. This expansion carries galaxies farther and farther apart, creating more and more empty space between them. Over vast timescales, this will mean that galaxies beyond a certain distance will slip beyond our cosmic horizon, never to be seen again. Already there are regions of the universe forever inaccessible to us, cut off not by walls but by the limits of light and time. This is another echo of what it means to live inside a black hole. Horizons are not barriers we bump into. They are limits on what can be observed, boundaries woven into the fabric itself. Scientists studying this expansion use equations that describe how the fabric stretches, and in doing so they find similarities to the equations that describe black holes. The same relativity that explains why Mercury's orbit shifts, or why clocks tick differently on mountaintops than at sea level, also explains the growth of space. And when applied to the cosmos as a whole, those equations suggest that our stage may be one of many, each formed inside its own horizon. This brings us back to the idea of relativity itself. Before Einstein, gravity was understood as a force, a mysterious attraction acting at a distance. Objects pulled on one another according to their masses, and the force was instantaneous, acting across empty space. It was a workable theory, but it left deep questions unanswered. Relativity replaced that picture with one in which mass and energy tell spacetime how to curve, and spacetime tells matter how to move. The beauty of this idea is that it is both simpler and stranger. Gravity is not a rope or a magnet. It is the natural motion of objects in curved space, and that curvature defines the very stage of existence. When we consider what it means to live inside a black hole, it is this curvature that matters most. The fabric of space within such a structure has a different geometry than the space outside. Time itself may flow differently. The dimensions may be arranged in ways that make sense only from within, and yet, to those inside, everything feels normal. Stars form, planets orbit, and life emerges. The stage is curved, but the play unfolds as if it were flat. That is the paradox of relativity. From within, reality feels ordinary even when, from outside, it is extraordinary. Another piece of this puzzle comes from energy. The universe is filled with matter and radiation, but it is also filled with something more elusive, something scientists call dark energy. This mysterious component seems to be driving the accelerated expansion of the cosmos, pushing galaxies apart faster than gravity can pull them together. Dark energy is woven into the fabric itself, not something that sits within space, but something that defines how space behaves. If our universe is inside a black hole, then dark energy may be the echo of the conditions that created it, a signature of the larger structure in which we are contained. This interplay between matter, energy, and the fabric of space gives the cosmic stage its form. It is not rigid, but flexible. It responds to what is in it, bends under its weight, and evolves over time. To live within it is to be carried along by its motions. We cannot stand outside and see the stage from another angle. We can only measure its curvature, trace its expansion, and infer its structure from the patterns we see in the sky. That is why black holes are such a powerful analogy. They too are regions where the fabric is curved beyond the ordinary, where horizons and singularity shape what can and cannot be observed. The more carefully we study the cosmos, the more evidence we find that our stage is indeed curved in a way that mirrors a black hole. The cosmic microwave background, the faint afterglow of the Big Bang, shows us how space was shaped in the earliest moments. Its tiny fluctuations map the fabric as it stretched and cooled, and the patterns match what relativity predicts for a universe born in a singularity. Every photon we detect from that ancient light is a clue to the geometry of our stage, and every clue points back to the same conclusion. Our fabric is not flat and unbounded. It has a history, a shape, and perhaps an enclosing horizon. This way of thinking forces us to reconsider our place in the cosmos. We often imagine ourselves as living in an infinite expanse, a stage without edges or limits. But relativity suggests that infinity may be an illusion, that what feels boundless from within may be bounded from without. To live inside a black hole would be to live inside such a bounded structure, one whose limits are unreachable but real, and that means our cosmic stage is not absolute. It is contingent, shaped by conditions we cannot directly see, and perhaps connected to larger realities beyond our own. As scientists continue to explore these ideas, they find themselves confronted with deep questions about the nature of space and time. Is the fabric continuous, or is it granular at the smallest scales? Does it emerge from something more fundamental, or is it the ultimate foundation of reality? If black holes can create new regions of space-time, does that mean the fabric is endlessly generative, spinning off new universes without end? These questions are not just abstract puzzles. They define what it means to exist at all, and so, when we talk about the fabric of space in the cosmic stage, we are not speaking in metaphors alone. We are describing the most basic features of reality, the structure that holds everything together, and the possibility that this structure is itself part of a larger whole. To live within it is to be part of its curvature, its horizons, its expansion. Whether or not we're inside a black hole, this fabric is our home, and if we are, then our home is part of an even greater stage, one whose contours we can only guess at, but whose existence makes our own possible. Gravity is something we live with so constantly that it can almost disappear from our awareness. It is the quiet force that holds us to the earth, that makes objects fall when we drop them, that gives weight to our bodies and shape to our movements. Most of the time it feels ordinary, almost dull compared to the flashier forces of nature like electricity or magnetism. But when you step back and look at the bigger picture, gravity reveals itself as one of the most mysterious and powerful influences in the cosmos. It is weak on the scale of a paperclip and a magnet, yet it dominates on the scale of planets, stars and galaxies. It is simple to describe. Everything with mass attracts everything else, yet nearly impossible to unify with the other forces of physics. And it is relentless, an endless pull that shapes the very fabric of space and time. To understand why gravity is so important to the idea that we might live inside a black hole, we need to trace its influence from the everyday world into the cosmic one. On Earth, gravity is measured by how quickly things fall, about 9.8 meters per second squared. It feels fixed, stable, something you can rely on. But even here, it is not uniform. Stand on top of a mountain, and gravity is slightly weaker. Move closer to the equator, and it is slightly less because of the Earth's rotation and bulge. Fly into orbit, and you are still under its influence, just in free fall. Gravity does not stop at the edge of the atmosphere. It stretches endlessly, growing weaker with distance but never vanishing entirely. In space, gravity is what keeps the moon tethered to the Earth, preventing it from flying away into the void. It is what holds the planets in their orbits around the Sun, each one moving in a delicate balance between inertia and attraction. For centuries, this was how gravity was understood, as a force acting between objects across empty space. Isaac Newton gave us equations to predict its effects, and those equations worked remarkably well. They could describe the motion of comets, the tides of the oceans, the fall of an apple. They gave us the confidence to chart the heavens and send spacecraft into orbit. But they also left a question unanswered. What is gravity really? How does one object reach across space to influence another without anything in between? Einstein's theory of general relativity reframed the question. Instead of being a force transmitted through nothingness, gravity became the manifestation of curved space-time. Mass and energy warp the fabric of reality, and objects move along the paths defined by that curvature. This is why planets orbit stars and why light bends near massive objects. They are not being pulled by an invisible hand. They are following the natural geometry of space-time itself. This way of thinking not only explained old mysteries but predicted new ones. Among those predictions were black holes, regions where the curvature is so extreme that all paths lead inward. Gravity's endless pull is what creates these objects. When a massive star runs out of fuel, there is nothing left to balance against gravity. The outward pressure of fusion vanishes and the star collapses inward. If the star is massive enough, no known force can stop the collapse. Gravity wins, and a black hole is born. From the outside, the event horizon forms, the point beyond which nothing can escape. From the inside, space-time itself is dragged inexorably toward the singularity. This is gravity not as a gentle tether, but as an unstoppable current, pulling everything into its depth. The strength of gravity is astonishing in such regions. Near the event horizon of a black hole, the pull is so strong that time itself slows. For an observer far away, clocks near the horizon appear to tick more slowly. For the person falling in, time feels normal, but the outside universe seems to speed up, racing ahead into the future. This strange warping of time is not science fiction. It is a real effect, confirmed by experiments even on Earth. Precise atomic clocks placed at different altitudes tick at slightly different rates because gravity is weaker at higher elevations. The difference is tiny but measurable. In a black hole, the effect is taken to an extreme. It is here that the idea of living inside a black hole gains its grounding. Our universe also experiences this stretching of time, this bending of space. Gravity is everywhere, shaping galaxies, clustering matter, and pulling on light. On the larger scales, gravity's endless pull competes with another mysterious influence, the accelerated expansion driven by dark energy. The balance between these two forces determines the fate of the cosmos. If gravity were stronger, the universe might eventually collapse back in on itself. If expansion wins, galaxies will drift ever farther apart, leaving an empty, cold void. The fact that we live in a universe finely balanced between these outcomes hints at a deeper structure, one that may involve black holes as more than just isolated objects. To live inside a black hole would mean that gravity's pull is not simply something that happens to stars or planets, but something that defines the entire cosmos. Our universe's expansion could be understood as the internal unfolding of such a region. The singularity at the centre would correspond to the Big Bang, the moment from which time and space began to flow. The event horizon would correspond to our cosmic horizon, the edge beyond which we cannot see. Gravity's endless pull would not just shape galaxies within the universe, it would define the universe itself, enclosing it in a structure we cannot escape. The thought may seem overwhelming, but in practice, it changes nothing about how we live day to day. We do not feel pulled toward the centre of the universe any more than we feel pulled toward the centre of a black hole from within. From our perspective, space stretches outward, time flows forward, and life unfolds normally. The pull of gravity is woven into everything we experience. It governs the tides, the orbits, the formation of stars, even the clustering of atoms in our bodies. Living inside a black hole would simply mean that all of this is taking place within a larger framework, one where gravity has already defined the boundaries. What makes gravity so fascinating in this context is its dual nature. On the one hand, it is familiar and constant, something you can test with a dropped ball. On the other hand, it is deeply mysterious, resisting all attempts to unify it with quantum mechanics, the framework that explains the other forces of nature. Gravity does not fit neatly into the equations of the very small. At the singularity of a black hole, our understanding collapses along with the matter. The two great pillars of physics, relativity and quantum theory, come into direct conflict, and neither can fully explain what happens. This is why black holes are considered laboratories for new physics. They are places where the endless pull of gravity forces us to confront the limits of our knowledge. Scientists have tried many approaches to reconcile these differences. Some propose that space-time itself is quantized, made of tiny discrete units, and that gravity emerges from their interactions. Others suggest that gravity is not a fundamental force at all, but an emergent property, a statistical effect of deeper processes. Still others turn to string theory, which describes particles not as points but as vibrating strings in higher dimensions. Each of these attempts aims to explain how gravity's endless pull fits with the rest of physics, and each draws inspiration from the behaviour of black holes. Because if we truly do live inside one, then understanding gravity is not just about distant stars. It is about the very stage of our existence. The endlessness of gravity's pull is not only about strength but about scope. No matter how far you go, no matter how empty the region of space, gravity is there. It may be faint, diluted by distance, but it never disappears. This universality is what makes it the architect of the cosmos. Gravity gathers gas into clouds, clouds into stars, stars into galaxies. It sculpts clusters and superclusters, weaving the web of cosmic structure. Without it, there would be no stars, no planets, no life. And in the end, gravity is what drives the collapse of massive stars into black holes. potentially seeding the birth of new universes. So when we talk about gravity's endless pull, we're talking about more than just a familiar tug. We're talking about the principle that shapes everything, from the fall of an apple to the birth of galaxies. If our universe is inside a black hole, then gravity is not just one of the forces at work within it. It is the defining feature of its creation, the reason there is a horizon, the reason there is an interior at all. Living inside such a structure means living in a cosmos born of gravity, sustained by gravity, and ultimately defined by gravity. When people speak of black holes, the phrase that often comes to mind is the point of no return. This is the event horizon, the invisible boundary that defines what is inside and what is outside. It is not a physical surface you could touch or bump into. It is not a wall of matter or a glowing shell. It is simply the region where gravity is so strong that not even light, the fastest thing in the universe, can escape. Once something crosses that threshold, its fate is sealed. To the outside world it disappears, never to be seen again. To the thing falling in, the crossing is almost unnoticeable. This paradox, this difference in perspective, is what makes the event horizon so fascinating and so important for the idea that our universe itself might lie inside one. The event horizon is a product of geometry, not material. It is defined by the curvature of space-time. When you solve Einstein's equations for a mass concentrated in a small enough volume, the result shows that there is a radius, a distance from the centre, where all possible paths point inward. Light, matter, energy, everything is drawn in. This radius is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who found the first exact solution to Einstein's equations in 1916. For a black hole the mass of the Earth, the radius would be less than a centimetre. For a black hole the mass of the Sun, it would be about 3 kilometres. For the supermassive black hole at the centre of our galaxy, the radius is about 12 million kilometres. What makes the event horizon so strange is that it is both absolute and relative. From the point of view of a distant observer, nothing ever crosses it. Objects falling toward the horizon appear to slow down, their clocks ticking ever more slowly, their light red-shifted into longer and longer wavelengths until they fade away. It looks as if they are frozen on the edge forever, but from the perspective of the object itself, nothing unusual happens at the horizon. It falls straight through, continuing on its journey, unaware that it has passed a boundary that cannot be undone. This duality is not a trick of perception, but a fundamental feature of relativity. Time and space are not the same for all observers. They depend on where you are and how you move. In a sense, the event horizon is not a place but a limit. It marks the boundary of information. Signals from inside cannot reach the outside. Events inside cannot influence what happens outside. It is this separation that makes black holes so mysterious. From the outside, they are defined entirely by 3 quantities: mass, spin, and charge. Everything else, the details of what fell in, the structure of matter, the history of collapse, is hidden behind the horizon. To use a phrase coined by physicist John Wheeler, black holes have no hair, they erase individuality. When scientists imagine our universe as the inside of a black hole, the event horizon becomes even more intriguing. In our cosmos, there is also a limit to what we can observe. The speed of light and the age of the universe combine to create a cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. Beyond that, the universe may continue, but it is forever hidden from view. We cannot receive signals from it, and it cannot influence us. This cosmic horizon plays the same role as the event horizon of a black hole. Both mark the edge of observable reality. Both separate what can be known from what is forever inaccessible. This parallel is one of the strongest hints that the idea of living inside a black hole may not be so far-fetched. Our cosmic horizon acts in the same way as the event horizon. From within, we see galaxies receding, red-shifting into invisibility as they approach the edge. Their light stretches out, fading away, just as an object falling toward a black hole appears to fade from the outside. The similarity is striking. It suggests that the cosmos itself may be enclosed in a horizon, an unseen boundary beyond which lies the larger structure that birthed it. The event horizon is not just a theoretical line, it has physical consequences. One of the most surprising discoveries of the 20th century came from Stephen Hawking, who showed that quantum effects near the horizon cause black holes to emit radiation. Particles and antiparticles are constantly forming and annihilating in the vacuum of space. Near the horizon, one can fall in while the other escapes, leading to a net emission of energy. This Hawking radiation is faint, far too small to observe for astrophysical black holes, but it has enormous implications. It means black holes are not eternal. They slowly lose mass and over unimaginable timescales evaporate away. It also raises deep questions about what happens to the information contained inside. Does it vanish, violating the rules of quantum mechanics, or does it somehow escape encoded in the radiation? This is the famous information paradox still unsolved today. For our universe, the analogy is suggestive. If our cosmic horizon is like an event horizon, might it also have quantum properties? Could our reality itself be the result of such processes, with information encoded at the boundary in a way we do not yet understand? This line of thought has led to the idea of the holographic principle, the suggestion that the entire volume of our universe might be described by information encoded on its boundary, just as the contents of a black hole are thought to be described by its horizon. If true, it would mean that the three-dimensional world we experience is, in some sense, a projection of information on a two-dimensional surface. This is not science fiction, but a serious idea pursued by physicists trying to reconcile gravity and quantum mechanics. Living inside a black hole would mean that our horizon is as fundamental as theirs. It is not a limit we can overcome with faster spacecraft or more powerful telescopes. It is a built-in feature of reality, a reminder that knowledge is bounded. The universe, vast as it is, has an edge to what can be seen, an edge not of matter, but of possibility. Beyond it lies something we can never touch, and yet, within it, we find everything we need to live, to think, to explore. The event horizon also forces us to confront the relativity of time. If you could hover safely just outside the horizon of a black hole, you would see the rest of the universe speed up. Stars would evolve, galaxies would collide, civilizations would rise and fall in what felt like moments. Meanwhile, to you, time would pass normally. Cross the horizon, and the outside universe would seem to accelerate even more, until all of eternity unfolded in a flash. This strange warping of perspective is built into the geometry, and when we consider our own universe, we see echoes of the same effect. At the cosmic horizon, time itself seems to behave differently, stretched by the expansion of space. The deeper we look into the universe, the further back in time we see. Distant galaxies are not just far away in space, they're far away in time. Their light has travelled billions of years to reach us, showing us the universe as it was long ago. Our horizon is a time horizon as much as a space horizon. This connection between space and time, between horizons and perspective, is central to the idea that our universe may be inside a black hole. It suggests that the structure we inhabit has the same qualities as those strange regions of space we thought were so distant and separate from us. The point of no return is not just out there. It may define our entire reality. It is important to remember that the event horizon is not a place of danger in itself. If you are falling into a supermassive black hole, the crossing of the horizon would be uneventful. You would not feel a bump or a flash. Only later, as you approach the singularity, would the tidal forces become destructive. For smaller black holes, those tidal forces, sometimes called spaghettification, would be felt even before crossing. But for the universe as a whole, the horizon is far beyond reach. It does not threaten us. It simply defines the stage we live on. To think of living inside a black hole is to accept that our event horizon is real, that there are limits to observation, and that those limits are structural, not temporary. The point of no return is not something we can cross or overcome. It is something that shapes our reality from the beginning. It gives us the observable universe, the domain within which we can study and live. Beyond it lies a mystery we cannot solve, just as beyond the horizon of a black hole lies a region hidden from the outside world. The parallels are so strong that many scientists find them hard to ignore. The horizon defines the black hole from the outside. The cosmic horizon defines the universe from the inside. Both are boundaries of knowledge, both are consequences of relativity, and both remind us that reality is larger than what we can see. To live inside one is to live with the horizon always at the edge of vision, always marking the limit of what can be known. At the very centre of a black hole lies the singularity, the place where the known laws of physics come to an end. It is often described as a point of infinite density, where all the mass of the black hole is concentrated. That description, though widely repeated, is more a signal of our ignorance than a complete picture of reality. Infinity in physics usually means that the equations we rely on have broken down, not that something literally becomes infinite. The singularity is a placeholder, a marker on the map of knowledge that says, beyond this point, we do not know what happens. Yet this marker is not just a minor detail. It is the central feature of a black hole, the reason horizons exist, the reason gravity becomes irresistible, and the reason scientists believe black holes may hold the key to understanding the deepest layers of reality. When we say matter collapses into a singularity, what we mean is that no known force can stop gravity from pulling it ever inward. In a neutron star, the collapse is halted by the quantum resistance of neutrons packed tightly together. But even that pressure fails when the mass is great enough. The star collapses further, beyond the limits of what we can model. In relativity, the result is a point where density and curvature become infinite. In quantum mechanics, such infinities are unacceptable. The two theories, each so successful in its own domain, clash at the singularity. That is why black holes are not just astronomical curiosities. They are the meeting ground of our two greatest theories, and they expose the fact that those theories cannot yet be reconciled. From the perspective of general relativity, the singularity is inevitable. Once matter collapses past the horizon, nothing can stop it from falling further. Space itself is tilted inward, and every path leads to the same conclusion. The singularity is not a place you can avoid, not a danger you can steer around. It is the future of everything that falls in. That inevitability gives black holes their character of finality, their sense of being cosmic traps. Yet, paradoxically, from the perspective of someone inside, the singularity is not immediately visible. It lies in the future, not the present. You cannot see it ahead of time, and you cannot communicate its presence to anyone else. It is only when you reach it that the breakdown occurs. In the context of our universe, the idea of a singularity takes on a different form. The Big Bang itself can be thought of as a kind of singularity, not in the sense of a collapsing star, but in the sense of a beginning beyond which we cannot see. The equations that describe the expanding cosmos trace back to a point where density and temperature become infinite. Just as with black holes, this infinity signals the failure of our models, not necessarily a physical infinity in nature. But the parallel is clear. Our universe began in a state where our theories cannot fully describe what was happening, just as matter falling into a black hole ends in such a state. One is the beginning of time, the other the end, and yet the mathematics connects them. This connection is what fuels the idea that our universe might be the interior of a black hole. If the collapse of matter in one universe leads to the birth of a new region of space-time, then the singularity is not just an endpoint. It is a bridge, a transformation. What looks like destruction from the outside looks like creation from the inside. For the larger universe, the collapse is the death of a star. For the inner universe, it is the birth of everything. In this way, the singularity becomes not only the heart of darkness, but also the source of light, the hidden place where one reality folds into another. Physicists have long struggled to describe what happens at singularities. Some approaches suggest that the laws of quantum mechanics must smooth them out, replacing the infinite point with a finite but extreme structure. Loop quantum gravity, for example, proposes that space itself is quantized, made of discrete units that cannot be divided further. In such a framework, the collapse would reach a limit where space can no longer be compressed. Instead of a singularity, there would be a bounce, a moment when contraction turns into expansion. From the outside, it would still look like a black hole, but from the inside, it would look like a new universe beginning with a big bang. Others turn to string theory, which replaces point-like particles with tiny vibrating strings in higher dimensions. In this view, the singularity might not be a point, but a complex structure where extra dimensions become relevant. The geometry of space-time could fold into shapes we cannot visualize, and the infinities of relativity would be resolved by the mathematics of strings. Still others suggest that the singularity is not a place at all, but a horizon of knowledge, a region where our language and concepts no longer apply. What lies beyond it may be inaccessible to us forever, not because it is not real, but because it is beyond what beings like us can perceive or measure. Despite these differences, the common thread is that singularities force us to confront the limits of science. They are not problems that can be patched over with small adjustments. They are signs that our most trusted theories are incomplete. Every attempt to unify relativity and quantum mechanics, every proposal for a theory of everything, is in some way an attempt to understand the singularity. That is why black holes are so central to physics. They are not just exotic objects in the sky, they are the testing grounds of reality itself. If our universe is indeed inside a black hole, then the singularity at its core is not something we will ever approach. It is not in our future, as it is for matter falling into a stellar black hole. It is in our past, in the moment of the Big Bang. We're already moving away from it, carried by the expansion of space. The singularity is not our doom, but our origin. It is the hidden heart of darkness from which all light and life emerged. In this sense, to live inside a black hole is to live inside the aftermath of a singularity, to inhabit the space-time it generated. What does this mean for us? It means that our everyday experience of the flow of time, the stability of space, the formation of stars and galaxies, is built on the foundation of something we cannot yet describe. The singularity lies beyond our science, yet it gave rise to the science we practice. It is both unreachable and inescapable, both hidden and central. Without it, there would be no horizon, no expansion, no cosmos to study. And yet with it, there are questions we cannot answer, mysteries we cannot penetrate. The singularity also challenges our notions of determinism. In classical physics, if you know the state of a system at one moment, you can predict its future. But at the singularity, the equations break down. The future cannot be predicted because the very structure of space and time ceases to exist. This unpredictability may be the seed of new universes. Each collapse could lead to a different outcome, a different set of laws, a different reality. From one perspective, this is unsettling. From another, it is liberating. It suggests that creation is not a singular event, but a process, ongoing, branching, endless. For scientists, the singularity is both a frustration and a lure. It frustrates because it refuses to yield to current theories, because it mocks our equations with infinities. It lures because it promises answers to the deepest questions. What is space made of? What is time? Why do the laws of physics take the form they do? To study black holes, to probe their horizons and their centres, is to reach for those answers. It is to acknowledge that we live in a universe built on a mystery, and that understanding it may transform everything we know. When Albert Einstein published his general theory of relativity in 1915, he could not have known how far its implications would reach. His goal was to describe gravity in a way that was consistent with the principle that the laws of physics are the same for all observers, no matter how they move. What he created was a framework not just for gravity, but for the structure of the universe itself. The heart of the theory lies in a set of equations, deceptively compact in appearance but almost limitless in depth. These are Einstein's field equations, which describe how matter and energy determine the curvature of space-time, and how that curvature in turn dictates the motion of matter and light. The equations can be written in a single line, but they are anything but simple. They balance the geometry of space-time on one side with the energy and momentum of matter on the other. Mass and energy tell space how to curve. Space tells matter how to move. With this elegant statement, Einstein reframed the cosmos. Gravity was no longer a mysterious force acting at a distance. It was the natural expression of geometry. Planets orbit stars not because they are being pulled, but because they are following the curved paths laid down by the fabric of space-time itself. It did not take long for physicists to realize that these equations predicted phenomena stranger than anything imagined before. Carl Schwarzschild, working from the trenches of World War I, found the first exact solution: the geometry of space-time around a point mass. That solution contained the seeds of what we now call black holes. At first, many dismissed this as a mathematical oddity. Surely nature would not allow such extremes. Even Einstein himself doubted that singularities could exist. But as time went on, evidence grew, and the reality of black holes became undeniable. The equations were not exaggerating. They were describing something real. What is striking about Einstein's equations is how open-ended they are. They do not dictate a single cosmos. They allow for many possibilities depending on the conditions. One set of solutions describes stars and planets, stable and balanced. Another describes black holes, collapsed and hidden. Still others describe entire universes, expanding or contracting, curved or flat. When applied to the cosmos as a whole, the equations give rise to cosmology, the study of the universe at its larger scales. The discovery that the universe is expanding, that galaxies are rushing apart, came directly from applying Einstein's framework. Without it, we would not have the Big Bang model. Without it, we would not understand the cosmic horizon, the microwave background, or the large-scale structure of galaxies. This flexibility is why scientists take seriously the idea that our universe itself could be the interior of a black hole. The equations allow for it. They describe not only the exterior view of a collapsing star, but also the possible interior view, where space-time continues beyond the horizon. From the inside, that continuation looks like an expanding universe. In fact, when you trace the solutions backward, the collapse on the outside maps onto a Big Bang on the inside. This is not an interpretation imposed from outside. It is what the mathematics itself suggests. Einstein himself resisted some of these implications. He was famously uncomfortable with the idea of an expanding universe. At first, he tried to force his equations into describing a static cosmos, one that neither expanded nor contracted. To do so, he introduced a term called the cosmological constant, a kind of repulsive energy that balanced gravity. Later, when observations showed that the universe is expanding, he called this addition his greatest blunder. Yet even this so-called mistake has returned in a new form. The accelerated expansion we observe today, driven by what we call dark energy, looks very much like a cosmological constant after all. Einstein's blunder may have been foresight in disguise. The field equations are like a fertile soil from which many different landscapes can grow. Among them are the exotic structures of black holes and the possibility of universes budding from them. The idea that our universe might be inside one is not idle speculation. It emerges naturally when you follow the equations into their most extreme regimes. They do not shy away from singularities. They predict them. They do not forbid horizons. They require them. And they allow for continuations beyond those horizons that look, from the inside, like entire expanding cosmoses. This openness has encouraged physicists to explore variations and extensions of the theory. Some study rotating black holes, described by the Kerr solution, which have not just one horizon but two, and a ring-shaped singularity. These solutions even allow for the possibility of wormholes, tunnels connecting different regions of space-time. Whether such structures can exist in reality is still uncertain, but the fact that they emerge from the equations shows how rich the possibilities are. Others study charged black holes, described by the Reissner Nordstrom solution, which introduce further complexity. Each of these solutions is like a window into a different aspect of what the equations can describe. When we step back and think about what it means to live inside a black hole, these solutions matter. They tell us that space-time is not limited to the simple, familiar forms we see in everyday life. It can twist, curve, and fold in ways that defy intuition. The interior of a black hole may not be a simple point of destruction, but a complex geometry that allows for the birth of new regions. Einstein's equations do not forbid this, they invite it. Another profound aspect of the equations is their universality. They apply everywhere, from the orbit of Mercury to the collision of galaxies. They have been tested in countless ways, from the bending of starlight during eclipses to the detection of gravitational waves from merging black holes. In every case, they hold true. This reliability gives scientists confidence that when the equation suggests something as strange as a universe inside a black hole, it is not to be dismissed lightly. It may be strange, but strangeness is part of the cosmos. The equations also highlight the connection between geometry and destiny. The fate of the universe depends on its curvature, which is determined by its energy content. If the density is high enough, the cosmos could eventually collapse back on itself in a big crunch. If it is low enough, it could expand forever, thinning out into cold emptiness. The balance between these outcomes depends on parameters encoded in the equations. And just as a black hole's interior is shaped by its mass and spin, our universe's evolution is shaped by its density and energy. The parallels are clear. Both are governed by the same framework. Both are possible outcomes of the same underlying rules. This raises a striking thought. If universes can be born inside black holes, then perhaps the equations describe not just one cosmos, but an endless branching of them. Each collapse could lead to a new expansion, each singularity to a new beginning. The equations do not set a limit on how many times this can happen. They allow for a multiverse, a vast tree of realities, each linked to the others by horizons and singularities. Our universe, in this view, is one branch on a tree without end. What makes Einstein's equations so extraordinary is not just their accuracy, but their openness. They describe the motion of planets with the same framework that describes the birth of universes. They connect the smallest scales we can measure to the largest we can imagine, and they do so with a simplicity that hides their depth. A handful of symbols contains within it black holes, horizons, singularities, gravitational waves, expanding space, and the possibility that reality is far stranger than we ever guessed. For scientists, working with these equations is both exhilarating and humbling. Exhilarating because they open doors to cosmic possibilities. Humbling because they reveal how limited our intuition is. We evolved to understand the motion of thrown rocks and flowing rivers, not the curvature of four-dimensional space-time. Yet the equations extend our vision, allowing us to grasp phenomena far beyond our senses. They are the reason we can even entertain the thought that we might live inside a black hole. Without them, such an idea would be fantasy. With them, it becomes a legitimate possibility. For much of the history of physics, black holes were thought of as the ultimate dead ends of the cosmos. They were regions where matter collapsed into oblivion, where energy was lost to the outside universe, and where nothing could ever escape. The name itself carries that sense of finality, a black hole, a place from which there is no return. And yet, as scientists have studied them more closely, a new picture has emerged. Instead of being the end of the story, black holes may be the beginning of a new one. They may not just swallow and destroy, but also create. They may be gateways, not endings, and through them new universes may be born. To understand this possibility, it helps to think about what actually happens when matter collapses into a black hole. From the outside, all we see is the event horizon forming. Matter falls in, light disappears, and the black hole's mass increases. The details of what fell in are erased, leaving only mass, spin, and charge to describe the black hole. But this is only half of the story. Inside, the equations of relativity suggest that space and time continue. They do not stop at the horizon. They evolve into a new region, a region that from the inside looks very much like an expanding universe. This is where the idea of black holes as gateways comes from. If the collapse of a star can create a new region of space-time, then each black hole might be the seed of a new cosmos. What appears as an end from one perspective becomes a beginning from another. The singularity, instead of being a final point of destruction, becomes a bridge, a transition. It is like walking through a doorway. From one side it is an exit, from the other it is an entrance. This possibility is more than just imagination. The mathematics of relativity allows it. Solutions to Einstein's equations describe not just the outside of black holes, but their potential interiors. Some of these solutions show space-time branching, with the collapse of matter leading to the birth of a new expanding region. To the outside universe, the black hole is a silent object growing in mass. To the inside universe, it is the moment of a big bang. This dual perspective is one of the most striking features of relativity. It shows us that what looks like destruction from one angle can look like creation from another. If black holes are gateways, then the cosmos is far richer than we once thought. Every black hole that forms could be the beginning of another universe. Some might be small and short-lived. Others might expand and grow into vast realities with their own galaxies, stars, and possibly even life. Our own universe could be one such offspring, born from the collapse of a massive star in a larger cosmos. This picture suggests that universes beget universes, that creation is an ongoing process, not a one-time event. For us, this changes the meaning of existence. If our universe is inside a black hole, then we are part of a chain of creation stretching beyond what we can see. The Big Bang was not the absolute beginning, it was the opening of a gateway. And just as we were born from such a process, the black holes within our own universe may be giving birth to others. The cosmos becomes a vast tree of realities, branching endlessly, each black hole a seed of a new branch. This raises fascinating questions about the laws of physics. Do all universes share the same laws, or do they differ? If the conditions inside a black hole set the properties of the universe it creates, then each new cosmos may have its own version of physics. Some might have different values for fundamental constants, different numbers of dimensions, or different balances between forces. Most of these universes might be inhospitable to life, but some, by chance, might be like ours. In this way, the existence of life may be tied to the generative nature of black holes. Universes that produce black holes give rise to more universes that do not simply fade away. Over time, this cosmic natural selection would favour universes like ours, rich in stars and galaxies, because such universes produce many black holes. Life would be a byproduct of this process, emerging in the universes most capable of reproducing themselves through black holes. This idea, sometimes called cosmological natural selection, is speculative but intriguing. It turns black holes from destroyers into creators, from dead ends into engines of cosmic fertility. Instead of being feared as the ultimate traps, they become the wombs of new realities. This reversal is one of the most profound shifts in perspective science has offered. It suggests that endings are not absolute, that every collapse may carry within it the seed of a beginning. For us, living in such a cosmos, the implications are both humbling and inspiring. It means that our universe may not be unique, but one among countless others. It means that the conditions that make life possible are not arbitrary, but part of a larger process. And it means that black holes, far from being exotic oddities, may be central to the story of existence. They are not just places where matter disappears, they are places where reality itself multiplies. The idea of black holes as gateways also helps us think about the mystery of singularities. If singularities are not true infinities but places where new spacetime begins, then they are not points of destruction but points of transformation. The equations of relativity do not forbid this, they hint at it. Quantum theories of gravity may one day describe the process in detail, showing how the collapse of matter in one universe becomes the expansion of space in another. Until then, the possibility remains open, supported by the parallels between black holes and our own cosmos. This gateway view also changes how we interpret the event horizon. Instead of being a final boundary, it becomes a threshold. From the outside, it marks the point of no return. From the inside, it marks the limit of what can be seen. Both perspectives are true, but together they suggest that horizons are not just barriers, they are doorways. They separate regions not of nothingness, but of new existence. To cross a horizon is to move from one domain to another, from one stage of reality to the next. Of course, we cannot test this idea directly. We cannot fall into a black hole and see whether a universe awaits on the other side. But we can compare the predictions of the equations with what we observe in our own universe. The similarities are strong enough that many scientists take the possibility seriously. Our cosmic horizon acts like an event horizon. Our Big Bang acts like a singularity. Our expansion acts like the interior of a black hole. The parallels are not superficial. They are structural. They suggest that what we call a universe may, in fact, be the inside of a gateway. To live inside such a gateway would not feel different from living in any other kind of universe. The stars would still shine, the planets would still orbit, and life would still unfold. The difference is in the context. Instead of being an isolated creation, our universe would be part of a larger chain, connected to others through the generative power of black holes. Every night sky would be not just a view of galaxies, but a reminder of the gateways scattered among them, each one perhaps giving rise to new realms beyond our sight. This perspective changes how we think about death and endings, not just for stars but for universes. The collapse of a star into a black hole looks final, but from another perspective it is the beginning of a new cosmos. The death of our universe, if it comes, may not be the end either, but the beginning of something else. Creation and destruction are not opposites, but two sides of the same process. Black holes show us this more clearly than anything else. As scientists continue to explore these ideas, they are driven by both evidence and imagination. Evidence, because the equations of relativity and the observations of the cosmos point toward these possibilities. Imagination, because stepping into them requires seeing reality in new ways. The possibility that black holes are gateways is one of the boldest ideas in modern science, but it is also one of the most natural. It takes the equations seriously, follows them to their conclusions, and accepts that the universe may be stranger and more fertile than we once thought. When scientists describe our universe as a bubble, they do not mean it in the sense of fragility or soap floating on air. The comparison comes from the way space-time itself can expand, forming a self-contained region separated from whatever lies outside. In cosmology, a bubble universe is a region where the conditions of physics allow space to stretch and grow, while outside that region the conditions may be different or even inaccessible. If our universe is the interior of a black hole, then it is just such a bubble, sealed off from the parent cosmos by the horizon, expanding within its own domain and evolving according to its own rules. The bubble analogy helps us picture what otherwise seems impossible. Imagine blowing a soap bubble. From the outside, you see a delicate sphere enclosing an interior. From the inside, if you could shrink yourself to the scale of an atom of air, the surface would appear distant and unreachable, and the space within would feel vast. That is our position within the cosmic bubble. We see galaxies receding, space stretching, and a horizon we cannot reach. To us, the bubble feels infinite. To an outside observer, if such a being could exist, it would appear as a finite region contained within a larger reality. Both views are true, but we only have access to the inside. The mathematics of relativity supports this picture. Solutions to Einstein's equations show that space-time can form enclosed regions, expanding from an initial singularity and separated from the outside by a horizon. These regions behave like bubbles, self-contained and evolving independently. If black holes create such regions, then each one is a bubble universe. Our own cosmos would be one such bubble, born from the collapse of a massive object in a larger cosmos. The event horizon of the black hole would serve as the surface of the bubble, preventing anything from passing out, while the interior expands and evolves. The bubble model also helps us think about why the universe looks the way it does. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, shows us that the early universe was remarkably uniform. The temperature was nearly the same in every direction, with only tiny fluctuations. This uniformity is puzzling if the universe is infinite and unbounded. How could regions so far apart have the same properties when they could never have communicated with one another? One answer is inflation, the idea that the universe underwent a brief period of rapid expansion in its earliest moments. Inflation smoothed out irregularities and made the cosmos uniform. It also reinforced the bubble picture, because inflation naturally creates bubble-like regions of space, each with its own properties. Our universe may be one such bubble among many, separated from the others by inflating space. If this is the case, then the larger reality is not a single continuous universe, but a multiverse, a vast collection of bubble universes, each isolated from the others. Some may be born from black holes, others may emerge from quantum fluctuations. Each bubble may have its own version of physics, its own laws, its own constants. Some might be sterile, expanding into emptiness. Others might be rich with galaxies and stars. Ours happens to be one that supports life, but it may not be unique. The bubble analogy also highlights the role of horizons. Just as the surface of a soap bubble separates the inside from the outside, the cosmic horizon separates our observable universe from the larger structure. We cannot cross it. We cannot see beyond it. From within, it looks like the edge of everything, but from the outside, it is just the boundary of one bubble among many. This is precisely how black holes behave. The event horizon looks like an end from the outside, but from the inside, it is simply the edge of a new space. The parallels are too strong to ignore. Living in a cosmic bubble does not change our everyday experience, but it does change the context of that experience. It means that the vast universe we see, with its billions of galaxies and trillions of stars, may be just one bubble in a frothing sea of universes. Each black hole in our cosmos may be another bubble budding off, hidden from us but real in its own right. This picture transforms the cosmos from a single stage into a vast network of stages, each playing out its own story. The bubble picture also suggests that beginnings are not absolute. The Big Bang, which we once thought of as the beginning of everything, may have been only the beginning of our bubble. Beyond it lies a larger reality, one that may have existed long before and may continue long after. Our bubble may expand, evolve, and eventually cool into emptiness, but the larger structure will go on, generating new bubbles in an endless cycle. This is creation not as a single event, but as a continuous process, bubbling without end. For scientists, this picture is both appealing and challenging. It explains some of the puzzles of cosmology, such as the uniformity of the cosmic microwave background and the fine-tuning of physical constants. But it also raises questions that may never be answered. If other bubbles exist, can we ever know them? If our universe is inside a black hole, can we ever detect the parent cosmos? The horizons that define bubbles are also barriers to knowledge. They limit what we can observe and test. We can infer, we can model, but we cannot see beyond. Still, the bubble model is a powerful way to think about the universe. It reminds us that what we see is not necessarily all there is. It opens the door to possibilities beyond our horizon. It connects the birth of our cosmos to the collapse of matter in another. And it shows us that black holes are not just objects within the universe, but maybe the seeds of universes themselves. Each bubble is a cosmos. Each horizon is a boundary of reality. And we, living within one, are part of a structure far larger than we can imagine. The bubble idea also invites us to think about time differently. Within our universe, time began at the Big Bang. But if bubbles are continually forming, then time in the larger structure has no beginning and no end. Universes rise and fall, bubbles expand and fade, but the process continues. Our time is local, bounded by our horizon. Beyond it lies a time we cannot access, a time that stretches beyond our bubble. To live in a bubble is to live in a local patch of reality, one chapter in a larger story. As we explore this idea, we begin to see the universe not as a singular creation, but as part of a vast landscape. Each black hole is a doorway, each bubble is a universe, and the multiverse as a whole is a sea of bubbles, endlessly forming and evolving. This picture may never be fully testable, but it emerges naturally from the mathematics of relativity and the observations of cosmology. It is not fantasy. It is a possibility written into the structure of physics itself. When we look at the night sky, the first impression is of stillness. The stars seem fixed in their places, the constellations steady over the years. But the truth is that the universe is in motion, restless on a scale too vast for us to notice with the naked eye. Galaxies are not static. They are moving apart, carried by the expansion of space itself. This discovery, made less than a century ago, changed our understanding of the cosmos forever. It told us that the universe has not always been the way it is today, that it had a beginning in the distant past, and that it will have a future shaped by the same expansion. And it gave us one of the strongest clues that our universe may be the interior of a black hole. The story of cosmic expansion begins in the 1920s, when astronomer Edwin Hubble made a careful study of distant galaxies. By measuring the light from these galaxies, he found that almost all of them are redshifted, meaning their light has been stretched to longer wavelengths. The more distant the galaxy, the greater the redshift. This was not an effect of the galaxies moving through space like ships drifting apart on an ocean. It was an effect of space itself stretching, carrying the galaxies with it. The universe was expanding. This discovery was revolutionary. Until then, most scientists believed the universe was static and eternal. The idea of expansion implied that the cosmos had once been smaller, denser, and hotter. If you run the expansion backward in time, you reach a point when all of space was compressed into a tiny volume. This was the birth of the Big Bang model, the idea that our universe began in a hot, dense state and has been expanding ever since. The expansion of the universe is not just a curious fact, it is a defining feature of our cosmos, one that mirrors the behaviour of black holes. Inside a black hole, space-time is not static. It evolves, stretches, and pulls everything inward toward the singularity. From the inside perspective, it can look like expansion, with distances increasing as space unfolds. The parallels are striking. Both the interior of a black hole and our universe are described by the same equations, the solutions of general relativity. Both involve horizons beyond which light cannot escape. Both have singularities where our understanding breaks down. One of the most important clues from expansion is that it is accelerating. In the late 1990s, astronomers studying distant supernovae found that galaxies are not just moving apart, they are moving apart faster and faster. This was a shock. Gravity should slow the expansion, pulling galaxies back together. Instead, something else is at work, something pushing space to expand more quickly. Scientists call this mysterious influence dark energy. Its nature is still unknown, but its effect is unmistakable. It behaves like a repulsive force, woven into the fabric of space itself, and it dominates the evolution of the cosmos. This acceleration makes the bubble analogy of the universe even more compelling. A bubble of spacetime expanding inside a black hole would naturally grow in this way, stretching faster as it evolves. The presence of dark energy may be a sign of the conditions that created our universe, the leftover imprint of the parent cosmos in which it formed. Just as the pressure inside a soap bubble determines its growth, the balance of energy in our universe determines its expansion. Another clue comes from the cosmic microwave background, the afterglow of the Big Bang. This faint radiation fills the universe, a remnant of the time when it was only 380,000 years old. It is astonishingly uniform, the same in every direction to within 1 part in 100,000. This uniformity is difficult to explain unless the universe expanded rapidly in its earliest moments, a period known as inflation. Inflation smoothed out irregularities and stretched space to such a degree that the cosmos looks flat and uniform on large scales. This inflationary expansion is exactly the kind of behaviour expected if our universe is a bubble inside a larger structure. It is another piece of evidence pointing toward the bubble model, and therefore toward the possibility that we live inside a black hole. The rate of expansion, known as the Hubble constant, is another clue, though one that comes with puzzles. Different methods of measuring it give slightly different answers, leading to what is called the Hubble tension. Some measurements based on nearby galaxies suggest a faster expansion rate, while others based on the cosmic microwave background suggest a slower rate. This discrepancy may be a sign that our understanding of cosmic expansion is incomplete, or that new physics is needed. One possibility is that the discrepancy reflects the influence of the larger structure our bubble is part of. If we are inside a black hole, the conditions of the parent cosmos could subtly affect the expansion we observe. Cosmic expansion also explains why there is a limit to what we can see. Because the universe has a finite age, light from beyond a certain distance has not had time to reach us. This forms our cosmic horizon, the boundary of the observable universe. Beyond it, space continues, but it is forever hidden. This horizon is another echo of the event horizon of a black hole. Both mark limits of observation, both are consequences of expansion. Both suggest that what we see is only part of a larger reality. Expansion shapes not only the larger structures but also the smallest details. The distribution of galaxies, the clustering of matter, the formation of stars, all depend on how fast the universe expands. If the expansion were slower, gravity would have pulled matter together more strongly, leading to a cosmos dominated by massive clusters. If it were faster, matter would have been diluted too quickly for galaxies to form. The fact that expansion is balanced in such a way that stars and planets exist is another clue. It suggests that our universe is one of many, and that its conditions are not arbitrary but selected from a larger range of possibilities. Black holes, as gateways to new universes, provide a natural explanation. Each universe would have its own expansion rate, its own balance of forces. Ours happens to be one where expansion allows for galaxies and life. The expansion also tells us about the fate of the universe. If it continues to accelerate, galaxies will eventually drift so far apart that their light can no longer reach one another. Stars will burn out, black holes will evaporate, and the cosmos will fade into cold emptiness. This scenario, sometimes called the heat death, is a natural consequence of expansion. Yet even in this bleak future, black holes suggest a new beginning. Each one may be a seed of another universe, a bubble budding from ours, carrying the process forward. The death of one cosmos may be the birth of another. Expansion, far from being the end, may be part of an eternal cycle. Scientists continue to measure expansion with increasing precision, using telescopes on the ground and in space. They map galaxies, study supernovae, and analyse the cosmic microwave background. Each measurement refines our picture of the cosmos, but each also deepens the mystery. Why is expansion accelerating? What is dark energy? Why do different methods give different results? These questions keep cosmologists busy, and the answers may point toward the larger structure of reality. If we're inside a black hole, then expansion is not just a property of our universe, it is the sign of the gateway through which we came. For us, expansion is not something we feel in daily life. Atoms, planets, and even galaxies are bound together by forces stronger than expansion. But on the larger scales, it shapes everything. It determines what we can see, what we can measure, and what the future will hold. To live in an expanding universe is to live in a bubble that is always stretching, always changing, always carrying us farther from the past. It is a reminder that stability is local, while motion is universal. The clues from expansion are compelling, because they connect so directly to the properties of black holes. Both involve horizons, both involve singularities, both involve stretching space and distorting time. The parallels are not accidental. They are built into the equations of relativity. They suggest that our universe, in expanding, is behaving exactly as it would if it were the interior of a black hole. Expansion is not just a feature of our cosmos. It is the signature of the gateway we pass through at the moment of the Big Bang. When we look out into the cosmos, one of the most striking things is how ordered it appears to be. Galaxies cluster into filaments and walls, stars form in spirals and disks, planets move in stable orbits, and the laws that govern their motion seem to be the same everywhere we look. It would be easy to take this for granted, to assume that the universe naturally has to look this way. But the truth is that the universe could have looked very different. The balance of forces, the values of fundamental constants, and the initial conditions of the cosmos all work together to create the reality we see. The question of why the universe looks the way it does is not trivial. It is central to understanding whether our universe is unique or one of many, and whether its features are signs that we live inside a larger structure such as a black hole. Consider, for example, the strength of gravity. If gravity were even slightly stronger, the universe might have collapsed back on itself long ago, stars burning too quickly for life to emerge. If it were slightly weaker, matter might never have clumped together into galaxies and stars in the first place, leaving the cosmos as a thin, diffuse mist. The strength of gravity is balanced in just the right way to allow long-lived stars, stable planets, and time for life to develop. This balance is not obvious or inevitable. It is one of the great puzzles of physics. The same is true for the electromagnetic force, which governs the interactions of atoms and molecules. If it were stronger or weaker by even a small fraction, the chemistry of the universe would be drastically different. Atoms might not form, or stars might not shine in the way they do. The fine structure constant, a number that measures the strength of this force, seems arbitrary, yet it is precisely the value needed for the complexity we see. Likewise, the masses of particles such as protons and neutrons, the ratio between matter and antimatter, and the properties of neutrinos all contribute to the structure of the universe. Change any of them even slightly, and the universe might look unrecognizable. This apparent fine-tuning has led many scientists to consider that our universe may not be unique. If black holes give rise to new universes, each one might have slightly different properties. Some universes would expand too quickly, others too slowly. Some would collapse before galaxies could form, others would remain empty. A few, by chance, would have the right balance for stars, planets, and life. In this view, the reason our universe looks the way it does is not because it was destined to, but because only universes with these properties can produce observers like us to notice them. It is a selection effect. Out of countless bubbles, we live in one that happens to support complexity. The large-scale structure of the universe also tells us why it looks the way it does. When we map galaxies across the sky, we see that they are not scattered randomly. They form filaments and clusters, woven together in a vast cosmic web. These structures grew out of tiny fluctuations in the early universe, variations in density that were imprinted in the cosmic microwave background. Over billions of years, gravity amplified those fluctuations, pulling matter into clumps, stretching filaments across space, and carving out voids between them. The pattern is beautiful, almost like lace, but it is also precise. Its properties depend on the balance of dark matter, dark energy, and ordinary matter. Too much of one or too little of another, and the web would look very different. Dark matter plays a central role here. Though invisible, it outweighs ordinary matter by more than 5 to 1. It provides the scaffolding on which galaxies form. Without it, stars would not cluster into galaxies, and galaxies would not hold together. Its presence is inferred from the way galaxies rotate, from the bending of light around clusters, and from the structure of the cosmic web. We do not yet know what dark matter is, but we know it is essential to the appearance of the universe. Again, the values matter. If dark matter were absent or too abundant, the cosmos would not look the way it does. Dark energy adds another layer of mystery. It drives the accelerated expansion of the universe, pushing galaxies apart faster than gravity can pull them together. Its effect determines the fate of the cosmos, whether it will expand forever, slow down, or collapse. It also influences the structure we see today, because the rate of expansion shapes how galaxies cluster. The fact that dark energy has just the right value to allow galaxies to form before pushing them apart is another puzzle. Why this value and not another? The universe looks the way it does because of this balance, but the balance seems delicate, as if tuned for the outcome we see. Even the shape of the universe depends on these factors. Measurements show that space is nearly flat, meaning that on large scales it does not curve inward or outward. A flat universe allows structures to form in the way we observe. A closed universe would have curved back on itself, while an open one would have expanded too quickly. The near flatness is explained by inflation, the rapid expansion in the early universe that smoothed out curvature. But inflation itself raises questions. Why did it happen? What triggered it? Why did it end when it did? The universe looks the way it does because inflation set the stage, but inflation is still not fully understood. On smaller scales, the formation of stars and planets adds further detail. Stars form when clouds of gas collapse under gravity, igniting nuclear fusion in their cores. The balance between gravity and pressure determines their lifespans. Small stars burn slowly, living for billions of years. Large stars burn quickly, ending in supernovae that scatter heavy elements into space. Those elements, forged in stellar cores, are the building blocks of planets and life. The universe looks the way it does because stars live long enough to create and distribute the ingredients of complexity. Without that balance, there would be no Earth, no oceans, no listeners to wonder about it all. The Earth itself is a product of these cosmic balances. The orbit of our planet lies in a zone where liquid water can exist, a narrow band around the Sun where conditions are neither too hot nor too cold. The tilt of the Earth's axis, the presence of the Moon, the balance of greenhouse gases all contribute to a stable climate. Each of these features is contingent, dependent on the history of our solar system and the broader conditions of the universe. The fact that life exists here is a reflection of the same question. Why does the universe look the way it does? Because it allows life, and because we are here to notice. From the perspective of black holes and bubble universes, the answer may be that we live in one of the rare universes where the conditions align. If black holes produce new universes with slightly different properties, then there is a vast landscape of possibilities. Most universes may be sterile. A few by chance have the right values. In this view, the fine-tuning is not a mystery to be solved, but a natural consequence of cosmic reproduction. Our universe looks the way it does because it is one of the successful ones, one where complexity and observers can arise. For scientists, this is both satisfying and incomplete. Satisfying because it provides a reason for the balance we see, incomplete because it leaves deeper questions unanswered. Why these laws of physics in the first place? Why is there something rather than nothing? Even if universes reproduce through black holes, what started the process? These are questions that may never be answered, but the search for answers shapes our understanding. In the meantime, we can marvel at the fact that the universe does look the way it does, that galaxies form webs, that stars shine, that planets orbit, that life exists. Each of these features is improbable on its own. Together they form a cosmos that is both comprehensible and mysterious. The clues are written in the sky, in the microwave background, in the clustering of galaxies, in the chemistry of life. They tell us that the universe is balanced in ways we're only beginning to understand. Time is one of those things that feels so familiar, so constant, that we rarely question what it is. We measure it with clocks, we feel it in the rhythm of our lives, and we sense it in the passing of days and years. Yet when we look at time through the lens of relativity and black holes, it turns out to be far stranger than we usually imagine. Inside a black hole, time behaves in ways that challenge intuition, stretching, slowing, and bending under the influence of gravity. And if our universe itself lies within such a structure, then the nature of time we experience may be deeply tied to the properties of a black hole. To begin, consider what happens near the event horizon. To an observer far away, time for something falling toward the horizon appears to slow down. The light emitted by the falling object becomes increasingly redshifted, stretched to longer wavelengths until it fades from view. From the outside perspective, the object never actually crosses the horizon. It just seems to freeze on the edge, growing dimmer as time slows to a halt. But from the perspective of the falling object itself, nothing unusual happens at the horizon. Time flows normally. The crossing is uneventful, unnoticed, and inevitable. This contrast illustrates a fundamental truth about time in relativity. It is not absolute. It depends on where you are and how you move. Inside the horizon, the strangeness deepens. In ordinary space, time points forward and space points outward. You can choose where to move in space, but you move through time in only one direction. Inside a black hole, these roles are reversed. The radial direction, the distance to the singularity, becomes like time. It is not a place you can avoid, but a future you must reach. No matter what you do, no matter which way you turn, your path carries you closer to the singularity. In this sense, falling into a black hole is like being swept into the future. The singularity is not a location you might dodge. It is a moment in your future that cannot be escaped. This reversal challenges our usual ways of thinking. Outside, time is universal enough that we can synchronize clocks, plan events, and share experiences. Inside, time is warped beyond recognition. Different observers may disagree completely about the order of events or the passage of duration. The closer you are to the singularity, the more extreme the distortion becomes, until eventually time itself, as we know it, ceases to have meaning. If our universe is the interior of a black hole, then our experience of time is already shaped by these distortions. The arrow of time, the sense that the past is fixed and the future open, may be a consequence of the geometry of space-time. The singularity at the Big Bang would act as the temporal origin, the point from which time flows forward. Just as objects inside a black hole inevitably move toward the singularity, everything in our universe inevitably moves forward in time. The arrow is built into the structure. It is not a separate law but a consequence of geometry. One of the great puzzles of physics is why time has an arrow at all. The laws of physics are, for the most part, symmetric. They work the same whether time moves forward or backward. Yet our experience is not symmetric. We remember the past, not the future. We grow older, not younger. Entropy increases, not decreases. This asymmetry is tied to the initial conditions of the universe. The Big Bang began in a state of extraordinarily low entropy, and since then entropy has been increasing. But why were the initial conditions so special? If our universe is inside a black hole, the answer may lie in the nature of the collapse that created it. The arrow of time may be inherited from the process of formation. from the way matter collapsed in the parent universe and gave rise to expansion in ours. Time inside a black hole is also tied to the concept of horizons. The event horizon marks a boundary not just in space but in time. From the outside, events beyond the horizon are forever in the future, unreachable. From the inside, the horizon marks the past, a surface you cannot recross. In our universe, the cosmic horizon plays a similar role. The light from beyond it will never reach us, not because of distance alone, but because time itself is structured so that it cannot. This temporal horizon shapes what we can know and experience, binding us to a finite region of space and a finite flow of time. The relativity of time near black holes has been tested even outside the context of cosmic horizons. Astronauts orbiting the Earth experience time more slowly than people on the ground due to both their speed and the weaker gravity at higher altitudes. The difference is tiny but measurable. GPS satellites must account for these relativistic effects to provide accurate positions. Near a black hole, the effect is magnified to extremes. Time slows dramatically, stretched by the curvature of space-time. This is not just a theoretical idea. It is a consequence of the same physics that makes satellites work. For us, living in a universe that may be inside a black hole, the implications are profound. It means that the flow of time we experience is not absolute, but contingent on the geometry of our cosmos. The ticking of clocks, the beating of hearts, the unfolding of history, all of it is embedded in a structure shaped by horizons and singularities. Time is not a universal river flowing outside of events. It is part of the fabric of space-time, twisted and curved by gravity, inseparable from the universe itself. This perspective also reshapes how we think about beginnings and endings. The Big Bang was not just a moment in time, it was the origin of time itself, the moment when the arrow began. Inside a black hole, the singularity marks the end of time for anything falling in. Inside our universe, the singularity of the Big Bang marks the beginning of time for everything within it. The symmetry is striking. In one case, time ends. In the other, time begins. But both are described by the same equations, the same geometry, the same structure. The mystery of time inside a black hole also points toward the need for new physics. Relativity describes how time bends and slows, but it does not describe what happens at the singularity. Quantum mechanics, with its probabilistic nature, adds another layer of complexity. To truly understand time in these extreme conditions, we need a theory that unifies relativity and quantum mechanics, a theory of quantum gravity. Such a theory may reveal that time is not fundamental at all but emergent, arising from deeper processes. If that is true, then the strangeness of time inside a black hole is not an exception, but a clue to its true nature. Some physicists have proposed that time may emerge from entanglement, the quantum connection between particles. In this view, the flow of time is tied to the growth of entanglement across space, a process that mirrors the increase of entropy. If so, then the arrow of time is built into the very structure of quantum reality. Inside a black hole, where entanglement plays a crucial role in Hawking radiation and the information paradox, this connection may be even more pronounced. Our universe, if it is inside a black hole, may inherit its temporal structure from these quantum processes. For us, the experience of time is personal and immediate. We wake, live, and sleep according to its rhythm. We age, we remember, we anticipate. Yet behind this familiarity lies a mystery as deep as any in science. Time is not the same everywhere. It bends near gravity, stretches near horizons, and may even cease to exist at singularities. The fact that we can live in a universe where time feels so stable is itself remarkable. It suggests that the balance of forces and conditions in our bubble universe allows for a coherent arrow of time, one that makes memory, causality, and life possible. The study of time inside black holes also raises philosophical questions. If time is relative, if it can slow and stretch depending on perspective, then what is the true nature of the present? Is there a universal now, or is the present different for every observer? Relativity suggests the latter. The present is not a single moment shared by all, but a slice of space-time unique to each observer. This idea is unsettling, but it is consistent with what we see. Time is personal, local, and relative. Inside a black hole, this relativity is magnified, showing us just how flexible and strange time can be. If our universe is inside a black hole, then the way we experience time is inseparable from that fact. The Big Bang was our horizon crossing, the moment when time began for us. The expansion of the universe is the unfolding of time within that horizon. The cosmic horizon is the limit of what time can reveal. All of it is structured by the geometry of space-time, just as it would be inside a black hole. Our arrow of time, our sense of past and future, is the product of the same laws that govern black holes. Entropy is one of those scientific words that sounds abstract but touches every part of life. At its core, it is a measure of disorder, a way of describing how systems move from organised states into less organised ones over time. A sandcastle slowly collapses into a pile of grains. A hot cup of tea cools to room temperature. A living being ages and eventually dies. These are all examples of entropy at work. It is not just a tendency, but a law, written into the second law of thermodynamics. In any closed system, entropy tends to increase, and it is this law that gives time its arrow, the reason we move from past to future, and not the other way around. To understand the arrow of time, think about why we remember the past but not the future. We can recall what has happened, we can store records, we can preserve memories. But the future is unknown, uncertain, always unfolding. This asymmetry is not explained by the basic equations of physics, which are, in most cases, time-symmetric. They work just as well forward as backward. The asymmetry comes from entropy. The past is the direction of lower entropy, the future the direction of higher entropy. The arrow of time is nothing more and nothing less than the universe's movement toward disorder. Black holes bring this connection into sharp focus. When physicist Jacob Bekenstein proposed in the 1970s that black holes have entropy, it was a radical idea. Until then, black holes were thought to erase information, swallowing everything without trace. But Bekenstein argued that black holes should have entropy proportional to the area of their horizons, not their volume. Stephen Hawking later confirmed this by showing that black holes emit radiation, slowly losing mass and energy over time. The entropy of a black hole is enormous, far greater than that of ordinary matter, and it is tied to the surface area of the horizon. This discovery linked black holes directly to thermodynamics, showing that they are not just gravitational objects but thermodynamic systems. The entropy of black holes is not just a curiosity, it is a clue to the fundamental nature of reality. It suggests that information is not destroyed, but encoded on horizons. It connects gravity, thermodynamics, and quantum theory in a way no other phenomenon does. And if our universe is the interior of a black hole, then its entropy, its arrow of time, and its expansion are all part of the same story. The universe began in a state of low entropy at the Big Bang. Since then, entropy has increased, driving the arrow of time. The fact that black holes have entropy tied to horizons suggests that our universe, with its cosmic horizon, may also have entropy tied to its surface. This is the basis of the holographic principle, the idea that the information describing our three-dimensional universe is encoded on a two-dimensional boundary. Entropy also explains why time feels irreversible. A shattered glass does not reassemble. Smoke does not return to a candle. The microscopic laws allow these things in theory, but the probability is vanishingly small. Entropy increases because there are more disordered states than ordered ones, and the universe naturally drifts toward them. This drift gives us the arrow of time, the sense that the future is different from the past. Inside a black hole, this arrow is absolute. The singularity is the ultimate state of high entropy, the unavoidable future of everything that falls in. Inside our universe, the arrow points toward increasing disorder as well, a reflection of the same principle. The low entropy of the early universe is one of the deepest mysteries in physics. Why did the Big Bang begin in such an ordered state? Why was the entropy so low compared to what it could have been? This special beginning is what gives us an arrow of time at all. If the universe had started in a state of maximum entropy, there would be no direction of time, no difference between past and future. The fact that we experience time as flowing is because the universe began in order and is moving toward disorder. If our universe is inside a black hole, this low entropy beginning may be explained by the collapse of matter in the parent universe. The conditions of that collapse could have set the stage for our ordered beginning, passing the arrow of time from one universe to the next. Entropy also plays a role in the fate of the universe. As time goes on, stars burn their fuel, galaxies spread apart, and black holes evaporate. Entropy increases until there is no more free energy to do work. This state, sometimes called the heat death, is a universe of maximum entropy, where nothing changes because everything is evenly distributed. It sounds bleak, but if black holes seed new universes, then even this end may be a beginning. The arrow of time in our universe may give rise to new arrows in others, each beginning with low entropy and evolving toward higher. Entropy does not end the story, it extends it. For us, entropy is not just a cosmic principle, it is present in everyday life. It is why we tidy our homes, why machines wear down, why energy is needed to maintain order. Life itself is a battle against entropy, using energy from the sun to maintain structure and complexity. Yet even life yields in the long run. The arrow of time is relentless, and entropy always wins. This everyday experience is a small reflection of the same law that governs black holes and universes. The same principle that scatters a deck of cards also shapes the fate of galaxies. The connection between entropy and information is another key clue. In physics, information is a way of describing the state of a system. Entropy is a measure of how much information is missing about the exact details. Black holes highlight this connection, because their entropy is enormous and tied to the amount of information hidden behind the horizon. This is why the information paradox is so troubling. If black holes evaporate, does the information vanish? If so, it would violate the fundamental law that information is conserved. Many physicists believe the information is somehow preserved, perhaps encoded in the Hawking radiation, perhaps on the horizon itself. Whatever the answer, it will reveal something deep about the relationship between entropy, information, and the arrow of time. If our universe is inside a black hole, then the cosmic horizon may play the same role. The information of our universe may be encoded on its boundary. Our arrow of time may be tied to the growth of entropy at that horizon. The increase of disorder inside may be mirrored by the properties of the horizon itself. In this sense, entropy is not just a measure of disorder, it is a measure of the structure of reality, the link between the inside and the boundary, between the flow of time and the fabric of space. The arrow of time also shapes how we think about causality. Events flow from past to future because entropy increases. Causes come before effects because order decreases into disorder. If entropy did not increase, the distinction between cause and effect would blur. Inside a black hole, causality is even more strict. The singularity is the inevitable future of everything inside. No cause can avoid its effect. In our universe, the arrow of time is more flexible but still unidirectional. We cannot change the past. We can only act in the present to shape the future. This asymmetry is part of what makes existence meaningful. Without an arrow of time, there would be no growth, no memory, no progress. Everything would be static, timeless, and lifeless. Entropy gives us history. It gives us change. It gives us the sense of moving forward. It also gives us mortality, decay, and impermanence. But those too are part of the fabric of reality. The arrow of time is not a flaw. It is the very structure that makes life possible. The study of entropy also shows how deeply connected everything is. The cooling of a star, the evaporation of a black hole, the melting of ice in a glass, all follow the same principle. They are not separate events, but expressions of the same law. Entropy is universal. It links the smallest scales to the largest, the everyday to the cosmic. It is a bridge between thermodynamics, information theory, and relativity. And it is central to understanding why the universe is the way it is, and why time flows the way it does. As we follow this thread, we see that entropy is not just about disorder. It is about the flow of information, the structure of horizons, and the arrow of time. It tells us why the universe began the way it did, why it evolves the way it does, and why it may give rise to new universes in the future. It is one of the deepest principles we know, and it is written into the fabric of black holes and cosmos alike. When scientists first developed quantum mechanics in the early 20th century, they were trying to explain phenomena that classical physics could not. The behaviour of electrons in atoms, the emission of light in discrete packets, the strange duality of waves and particles. These were mysteries that Newton's laws and even Maxwell's equations could not account for. Quantum mechanics brought a new framework, one that replaced certainty with probabilities, replaced rigid determinism with possibilities, and introduced concepts so strange that even its founders admitted they did not fully understand them. Yet despite its strangeness, quantum theory is the most accurate and successful framework we have for describing the microscopic world. At the same time, general relativity described the macroscopic world with equal success. It tells us how space and time bend, how gravity shapes the cosmos, and how black holes form. But the two theories do not fit together. Relativity treats space-time as smooth and continuous. Quantum theory treats the world as discrete and uncertain. At the singularities of black holes, the two collide, and neither can give a full answer. This clash is why physicists seek a theory of quantum gravity, a framework that unites the insights of relativity and quantum mechanics. One of the paths towards such a theory involves hidden dimensions. In string theory, the particles of nature are not points, but tiny vibrating strings. The different vibrations correspond to different particles: photons, electrons, quarks, gravitons. But for the mathematics to work, string theory requires extra dimensions of space. Not just the 3 we experience, but 6 or 7 more, curled up so tightly that we cannot perceive them. These hidden dimensions, though invisible, may be essential to reality. They could explain why forces have the strengths they do, why particles have their properties, and why the universe looks the way it does. If our universe is inside a black hole, hidden dimensions take on even more significance. The collapse that formed our cosmos may have involved these dimensions, shaping the conditions of the Big Bang. The singularity may not be a point of infinite density, but a region where extra dimensions unfold. What looks like a breakdown of relativity may be a signal that deeper structures are at play. In this view, black holes are not just exotic objects, but windows into higher dimensions. Their horizons and singularities may be places where hidden dimensions reveal themselves. Quantum theories also suggest that information is never lost. This is one of the central debates about black holes. If matter falls in, does its information vanish at the singularity, violating quantum laws, or is it preserved in some way? The holographic principle, inspired by black hole entropy, suggests the latter. It proposes that all the information in a volume of space is encoded on its boundary, like a hologram projecting a 3-dimensional image from a 2-dimensional surface. If true, then our universe may itself be a hologram, with its 3-dimensional reality emerging from information encoded on a distant surface. The connection between black holes, entropy, and holography ties directly into quantum theories and hidden dimensions. In some versions of string theory, our universe is a 3-dimensional membrane, or brane, floating in a higher dimensional space. Black holes in this framework may connect branes, or give rise to new ones. Our cosmos could be one brain inside a black hole formed on another. Hidden dimensions would not be abstract mathematics, but real structures shaping the birth and evolution of universes. What we see as a Big Bang might be, from another perspective, the budding of a brain from a higher dimensional collapse. Quantum mechanics also introduces the idea of uncertainty, the principle that you cannot know both the position and momentum of a particle with absolute precision. This uncertainty is not a flaw but a feature. It is built into the fabric of reality. Even empty space is not truly empty, but filled with fluctuations, particles popping in and out of existence. Near the horizon of a black hole, these fluctuations give rise to Hawking radiation, the slow evaporation of black holes. This connection between quantum uncertainty and horizons reinforces the idea that black holes are laboratories for new physics. If our universe is inside one, then the uncertainty and fluctuations we observe may be reflections of its quantum origins. Another approach to quantum gravity is loop quantum gravity, which suggests that space itself is quantized, made up of tiny loops woven into a network. In this picture, space is not continuous but discrete at the smallest scales. The singularity of a black hole would not be an infinite point but a bounce, where collapse turns into expansion. Our universe could be the result of such a bounce, born inside a black hole when quantum geometry prevented total collapse. The arrow of time in our cosmos would be inherited from this process, the unfolding of spacetime from a quantum transition. These theories, while different in detail, share a common theme. They suggest that reality is deeper than what we see, that hidden dimensions or quantum structures underlie the familiar fabric of space and time. They point to black holes as the places where these deeper structures become visible, where relativity and quantum mechanics meet. And they suggest that our universe, with its horizons, expansion, and arrow of time, may be the inside of a black hole shaped by these hidden dimensions. For us, living in such a universe would not feel unusual. The hidden dimensions would be curled up too tightly to perceive. The quantum structure of space would be too fine to notice. Our everyday world would seem continuous and three-dimensional. But beneath the surface, the deeper reality would be there, shaping everything. The strength of forces, the properties of particles, the expansion of the universe, all would be determined by these hidden structures. We would be like fish in a pond, unaware of the water molecules around us but entirely dependent on them. Quantum theories also suggest that space and time themselves may not be fundamental. They may emerge from entanglement, the quantum connection between particles. In this view, the geometry of space is built from patterns of entanglement, and time emerges from the growth of entropy. If true, then the strangeness of time inside black holes is a clue to its emergent nature. Our universe, if it is inside a black hole, may be a large-scale manifestation of these processes, with space and time themselves arising from quantum connections across hidden dimensions. The idea of hidden dimensions also expands our sense of possibility. If other dimensions exist, then other universes may exist as well, separated from us by barriers we cannot cross. Black holes could be the bridges connecting dimensions and spawning new realities. Each hidden dimension adds richness to the cosmos, layers of structure beyond what we can see. Our universe may be just one of many, each with its own dimensional structure, its own laws, its own arrow of time. For scientists, exploring these ideas is both a challenge and a thrill. The mathematics is complex, the experiments indirect, the evidence elusive. Yet the stakes are high. To unify relativity and quantum mechanics, to understand black holes and singularities, is to reach for the foundations of reality itself. Hidden dimensions, holography, quantum geometry. These are not just abstract speculations. They are attempts to make sense of the clues nature has given us, from the entropy of black holes to the expansion of the cosmos. For us, the significance is profound. It means that the universe we see may be only a slice of a deeper reality. one shaped by quantum structures and hidden dimensions, it means that the flow of time, the structure of space, and the existence of universes may all be emergent phenomena, not absolutes. It means that black holes, far from being dead ends, are doorways to understanding. When we speak about the universe, we usually mean everything that exists, the totality of space, time, matter, and energy. By definition, it feels like there can only be one. Yet modern physics increasingly entertains the possibility that our universe is not alone. There may be others, separate from ours, unreachable, but real. Together, they would form what scientists call a multiverse, a vast ensemble of universes, each with its own properties and histories. If black holes give rise to new universes, as some theories suggest, then we live not in a singular cosmos, but in a nested structure. One universe inside another still. The idea of other universes is not new. Philosophers have speculated for centuries about multiple worlds, parallel realities, and infinite possibilities. But only in the last 100 years has physics provided concrete reasons to take the idea seriously. One of the strongest comes from inflation, the rapid expansion that smoothed the early universe. Inflation, once it begins, does not end everywhere at once. It continues in some regions, creating new bubble universes while others stop inflating and evolve into galaxies and stars. This process, called eternal inflation, naturally creates a multiverse. Each bubble is a universe. Some may have different laws of physics, different constants, or different numbers of dimensions. Our universe would be just one bubble in this endless froth. Black holes offer another route to a multiverse. If each collapsing star creates a new region of space-time, then black holes are not endpoints, but seeds. Every black hole in our universe could be a portal to another universe inside, each with its own expansion, its own galaxies, its own arrow of time. Our own universe could be the interior of a black hole in another cosmos, which itself may be inside yet another. This nesting could continue indefinitely, like a set of Russian dolls, each universe contained within the horizon of another. What would it mean to live in such a structure? From within, each universe would appear complete, with its own laws, its own horizons, its own history. The beings inside would see galaxies and stars. They would measure the flow of time. They would develop theories about their origins. Yet they would never see beyond their own horizons. They would never know directly of the larger structure in which they are embedded. To them, their universe would seem self-contained. Only by looking at clues, the expansion, the entropy, the fine-tuning of laws, could they suspect that there is more beyond. That is our situation. If universes can be born inside black holes, then the number of universes may be unimaginably large. Every galaxy has millions of black holes. The observable universe has trillions of galaxies. The number of potential universes budding off from them is beyond counting. Some of these universes may be short-lived, collapsing soon after formation. Others may expand for billions of years, forming stars and planets. A few may develop the conditions for life. From this perspective, our universe is not unique, but one among countless realities, one thread in a vast tapestry. The idea of nested realities also raises the question of whether the laws of physics are universal. In our universe, the speed of light, the strength of gravity, the charge of the electron, these are constants we take as given. But in other universes, they might be different. Some may have stronger gravity, leading to rapid collapse. Some may have weaker forces, leading to diffuse emptiness. Some may have dimensions arranged in ways we cannot imagine. The multiverse allows for diversity, with each universe exploring a different set of possibilities. We happen to live in one that supports complexity, but there may be others that do not. This perspective also offers a possible explanation for why our universe looks so finely tuned for life. The delicate balance of forces and constants is unlikely to have arisen by chance in a single universe. But if there are countless universes, each with different properties, then it is not surprising that at least one would have the right conditions. We live in that one because only in such a universe could beings like us exist. This is sometimes called the anthropic principle, the idea that our observations are biased by our existence. It is controversial, but it becomes natural in a multiverse of nested realities. If our universe is inside a black hole, then we are part of a chain of universes connected by horizons and singularities. Our universe may itself contain countless black holes, each giving rise to new universes in turn. This chain could extend without end, with universes creating universes, each generation passing on its properties to the next. Some have even suggested that this process may involve a kind of natural selection. Universes that produce many black holes would give rise to more offspring, while those that do not would fade away. Over time, the multiverse would become dominated by universes like ours, rich in stars and black holes. Life may be a byproduct of this cosmic reproduction, emerging naturally in the universes best suited to sustain it. For us, living in a nested reality would not feel different from living in a standalone universe. Our sky would still show stars and galaxies. Our physics would still describe the motion of matter and the flow of time. But the context would be larger, the story deeper. Instead of being the totality, our universe would be a part, a chapter in an ongoing process of creation. The Big Bang would not be the ultimate beginning, but the beginning of our particular bubble. The end of our universe, if it comes, may not be final either, but the seed of something new. The idea of nested realities also reshapes our sense of scale. We often think of the universe as the largest possible thing, the ultimate container of all else. But if it is a bubble inside a larger cosmos, then it is not the largest after all. There may be structures beyond our horizon, dimensions beyond our reach, layers of reality stacked one within another. Each layer would feel complete to those within it, but each would be part of something greater. The true scale of existence may be far beyond what we can comprehend. For scientists, exploring these ideas requires both imagination and rigour. Imagination, to conceive of universes beyond our own. Rigour, to ground these ideas in equations and evidence. The parallels between black holes in our universe, the clues from expansion, the fine-tuning of constants, the structure of entropy. These are the threads that suggest nested realities. They do not prove it, but they make it plausible. The mathematics of relativity and quantum theory allow for it. The observations of cosmology hint at it. Together they point toward a larger picture. For us, the significance is profound. To live in a nested reality is to be part of an endless process, a chain of creation that stretches beyond our horizon. It means that our universe is not alone, that there are others, perhaps infinitely many. It means that what we see is not the whole, but a part, a bubble in a larger froth. And it means that black holes, far from being the end of the story, are the places where the story continues, the gateways to new realities. We can describe the mathematics, the horizons, the entropy, but what would the experience be? If our universe is inside a black hole, what does it mean for life, for perception, for the way reality appears to us? When we think about black holes, it is natural to picture them as hostile places, regions of immense gravity where nothing can escape, where light itself is trapped, and where any object that wanders too close is torn apart. This image is correct in one sense, but it misses something important. For anyone actually inside a black hole, the experience might not feel violent at first. In fact, if our entire universe is the inside of a black hole, as some scientists suggest, then living inside one is not something extraordinary at all. It is simply existence as we know it. Galaxies, stars, planets, and life could all unfold in such a setting, with no sense of danger, no awareness of horizons or singularities, only the perception of a vast and ordinary cosmos. To imagine what living inside a black hole would feel like, it helps to start with the distinction between outside and inside. From the outside, a A black hole is defined by its event horizon. Nothing that passes through can return. Time for an object falling in appears to slow to a halt, its light stretched into invisibility. To an external observer, the black hole is a one-way trap. But from the inside, the experience is entirely different. Crossing the horizon is uneventful. There is no barrier, no wall, no sudden change. You simply pass through, and life continues. This is crucial. If our universe is inside a black hole, we would not notice the horizon around us. It would be beyond reach, forever out of sight, just as our cosmic horizon is. From our perspective, the universe would seem open and infinite, even though it is bounded. Inside, the most important difference is the nature of time. The direction toward the singularity is not a place you can avoid. It is the future itself. Just as you cannot avoid moving forward in time, you cannot avoid moving closer to the singularity. This does not mean you feel pulled or dragged. It means that the very geometry of space-time defines your path. You live, you move, you experience, and all the while you are carried forward. If our universe is inside a black hole, the Big Bang was the singularity in our past, and everything since has been the unfolding of time away from it. From our perspective, it feels natural, like the steady flow of moments. The scale of experience is another key. On the level of stars, black holes can be destructive. Falling into a stellar mass black hole would expose you to tidal forces so strong they would stretch and tear matter apart, an effect often called spaghettification. But on the scale of supermassive black holes, such as the ones at the centres of galaxies, the horizon is so vast that tidal forces at the boundary are gentle. An object could cross without noticing anything unusual. If our universe is inside a black hole, it would almost certainly be one of these enormous ones, large enough to allow entire galaxies and stars to exist peacefully within. Living inside would not feel like danger. It would feel like life, unfolding in an ordinary cosmos. One of the most striking aspects of living inside a black hole would be the presence of horizons. We would never be able to see beyond a certain distance. Light from regions farther than our cosmic horizon would never reach us. To us, it would seem as if the universe simply ends there, not with a wall, but with emptiness. Beyond that horizon, other regions may exist, but they are forever inaccessible. This is exactly what we observe. The observable universe is finite, bounded by the horizon, set by the age of the cosmos and the speed of light. Beyond it, the universe may continue, but we cannot know. This limitation would be part of living inside a black hole. It would not feel like a restriction. It would simply define what we can observe. What about the singularity? From the inside, it is not something you approach in daily life. It is not a place you can see or avoid. It lies in the past, at the Big Bang. We are already moving away from it, carried by the expansion of space. For us, it is not a threat, but a memory encoded in the structure of the cosmos. The radiation of the cosmic microwave background is a faint echo of that moment, the afterglow of the singularity. Living inside a black hole means living in the aftermath of such a beginning, with no awareness of the singularity itself. It is always there, shaping the geometry, but it is not part of daily experience. If we imagine what it would feel like to live inside a black hole more directly, we can think about the familiar experiences of time and space. Time would feel normal, flowing forward, carrying us through moments. Space would feel vast, filled with galaxies and stars. Gravity would work as expected, binding planets to stars, stars to galaxies. The laws of physics would be the same, governing matter, energy, and light. In short, life would feel ordinary. The extraordinary nature of living inside a black hole would be invisible, hidden behind the horizon, encoded in the geometry of space-time. There are subtler differences, though. The expansion of the universe, which we observe as galaxies moving away from us, would be a sign of our interior status. This expansion would not feel strange. It would simply look like galaxies receding, like space stretching. But in the context of black holes, it would be the natural unfolding of the interior. The acceleration of this expansion, driven by dark energy, may even be a reflection of the conditions of the larger cosmos. Living inside a black hole, we would experience expansion as a basic fact of life, not realizing it is the signature of a deeper structure. Another aspect of experience would be the arrow of time. We always move forward, never backward. We remember the past, but not the future. We see order dissolve into disorder, never the reverse. This arrow is built into the structure of the black hole interior. The singularity defines the past. Entropy increases toward the future. The direction of time is as absolute as the direction toward the singularity. Living inside a black hole, we would feel time as a steady progression, unaware that its arrow is tied to the geometry of the cosmos itself. If black holes give rise to new universes, then our experience of living inside one may be echoed in countless other realities. Beings in those universes would feel the same normalcy. They would see stars and galaxies, measure time and space, and wonder about their origins. They would not see the horizon around them or the singularity behind them. They would live as if their universe were all there is. In this sense, living inside a black hole is not an extraordinary experience, but the most ordinary one. It is life as we know it. Yet the idea adds a layer of wonder to everyday existence. To think that the stars above us are shining inside the interior of a black hole. To imagine that our universe is a bubble enclosed by a horizon. To realize that our arrow of time is the flow away from a singularity. These are not experiences we feel directly, but they reshape how we understand our place in the cosmos. Living inside a black hole would not feel different. But knowing it might be true changes everything about how we see the universe. For us then, the feeling of living inside a black hole is a paradox. It feels ordinary because life unfolds normally, but it feels extraordinary when we realize the context. The sky, the galaxies, the flow of time, and the expansion of space all may be the signs of our interior existence. We live as if in a room without windows, never seeing beyond, but filled with light and life within. The horizon is our wall, the singularity our past, the expansion our future. This is what it means to live inside a black hole. From the moment we are born, our understanding of the world is shaped by our senses. We see with eyes tuned to a narrow band of light. We hear vibrations of air within a limited range. We feel textures and temperatures within the tolerance of our nerves. These senses are astonishingly powerful, allowing us to navigate life, build civilizations, and explore the cosmos. Yet they are also profoundly limited. We perceive only a sliver of what exists. The greater part of reality lies beyond our reach, hidden from our direct awareness. This is true in the smaller scales of atoms and particles, and it is true in the larger scales of galaxies and universes. If our cosmos is inside a black hole, then our limits of perception become even more striking, because the very structure of reality is bounded by horizons we can never cross. Our eyes, for example, detect wavelengths of light between roughly 400 and 700 nanometers. This is the visible spectrum, the rainbow of colours from violet to red. Beyond that lie ultraviolet and infrared, which we cannot see. Beyond those are radio waves, microwaves, X-rays, and gamma rays. All of these are forms of light, electromagnetic radiation, yet our vision is blind to them. Only with instruments do we glimpse them, and when we do, our view of the universe changes dramatically. Radio telescopes reveal cold hydrogen clouds and pulsars. Infrared telescopes show warm dust and star-forming regions. X-ray telescopes expose violent collisions and black holes themselves. Each window adds a layer of understanding, but even combined, they show only part of the whole. Our ears are similarly limited. We hear vibrations between about 20 Hz and 20,000 Hz. Frequencies lower than that are infrasound, felt more than heard, used by elephants to communicate over long distances. Frequencies higher than that are ultrasound, used by bats to navigate and by doctors to image the inside of the body. Sound itself requires a medium, so in the vacuum of space there is no sound at all. The universe is silent to our ears. We must translate radio waves into sounds to make them audible, but they are not sounds in the ordinary sense. Our perception of the cosmos is filtered not only by range but by medium. Touch, taste and smell connect us to the immediate world, but they are parochial senses, limited to the environment around us. They tell us little of distant galaxies or hidden dimensions. Even when extended by technology, they remain local. A probe can touch the surface of a comet. A rover can taste Martian soil, but these are isolated glimpses. The larger cosmos remains beyond their reach. This is why science depends so heavily on instruments, telescopes, detectors, particle accelerators, satellites. These extend our senses, allowing us to perceive what we otherwise could not. They are prosthetics for the mind, widening the narrow window of human perception. Yet even with them, there are limits. The speed of light sets a horizon on what we can see. The age of the universe sets a boundary on how far signals can reach us. The cosmic horizon is the ultimate limit of perception. Beyond it, there may be galaxies, structures, even other universes, but we will never know. Their light will never reach us. Their signals will never arrive. They are forever outside our perceptual reach. This is where the analogy with black holes becomes powerful. Just as we cannot see beyond the cosmic horizon, an outside observer cannot see into a black hole. Horizons are not just distances. They are boundaries of knowledge. They mark the limits of perception. To live inside a universe that may itself be a black hole is to live inside such a bounded domain. Our senses, even extended by instruments, cannot cross that boundary. We are confined to what is inside, and the outside remains hidden. Even within our horizon, our perception is limited by scale. At the smallest scales, quantum mechanics rules. Particles flicker in and out of existence. Positions and velocities blur into probabilities. Entanglement connects distant points in ways that defy classical intuition. These phenomena are real, but we cannot perceive them directly. Our senses evolved for survival in a macroscopic world, not for perceiving the quantum foam. At the larger scales, galaxies cluster into webs stretching across billions of light years, but we can only map them faintly, like cartographers sketching coastlines from fragments. Our instruments give us glimpses, but the full structure remains beyond direct perception. Our brains, too, impose limits. We evolved to notice patterns relevant to survival, faces, movements, sounds of danger. We did not evolve to intuitively grasp four-dimensional spacetime, quantum uncertainty, or hidden dimensions. These concepts strain our imagination because they lie outside the range of what perception and intuition were shaped to handle. We can model them mathematically, simulate them on computers, and visualize them abstractly, but we cannot feel them directly. To us they remain strange, even when we understand them intellectually. If our universe is inside a black hole, then these limits are not accidents. They are structural. The horizon sets an absolute boundary on perception. The singularity lies forever in our past, unreachable except through its faint echoes. The expansion of space carries galaxies beyond sight, not because of distance alone, but because of the geometry of the cosmos. Our experience of reality is bounded not only by our senses, but by the architecture of the universe itself. We are like observers in a room with walls too distant to see, yet walls that still enclose us. And yet, within these limits, we build meaning. We study what we can see, we measure what we can detect, and we infer what lies beyond. This is the power of science. Not to eliminate limits, but to work within them, to push against the boundaries of perception with reason and imagination. We may never see beyond the cosmic horizon, but we can model what might lie there. We may never experience hidden dimensions, but we can deduce their necessity from the behaviour of particles. We may never witness another universe, but we can find clues in the expansion of our own. For us, the limits of perception are not failures. They are the conditions of existence. They remind us that reality is always larger than what we can know. They encourage humility, showing us that our senses, our instruments, even our theories capture only a fragment of the whole. They also inspire wonder, because the very act of glimpsing beyond those limits, of seeing galaxies billions of light years away, of detecting gravitational waves from colliding black holes, of measuring fluctuations in the cosmic microwave background, is extraordinary. Each discovery pushes back the boundary, even if the ultimate horizon remains. Living inside a black hole, if that is indeed our condition, would feel like living inside any universe, ordinary, bounded, full of life and change. But the recognition of limits would be sharper. We would know that beyond our horizon lies something we can never touch. We would know that our perception is not the measure of all that exists. We would know that reality is layered, nested, and richer than our senses suggest. If we can never see beyond our horizon, can we ever know the full truth about reality? If our senses are so limited, can our theories ever be complete? When we think about the possibility that our universe might be the inside of a black hole, the discussion is not only about physics. It inevitably drifts into philosophy, because the implications touch on questions that go beyond equations and experiments. What does it mean to live in a reality that is not all there is? What is the nature of beginnings and endings? Can we ever know the truth about the larger structure in which we may be embedded? Or are we forever confined to our own horizon? These are questions that blur the line between science and philosophy, because they concern not only what the universe is, but also what it means for us to be part of it. One of the deepest philosophical questions raised by black holes and cosmology is whether reality has an ultimate foundation. In everyday life, we assume that things have explanations. If a glass breaks, we can explain it in terms of gravity, impact, and material stress. If a star shines, we explain it with nuclear fusion. If the universe exists, we naturally ask what caused it. But if our universe is inside a black hole, then the answer may be that it was caused by the collapse of matter in another universe. That in turn may have been caused by a collapse in a universe before it, and so on, in a potentially endless chain. Does the chain have a beginning, or does it go on forever? If it goes on forever, is that an explanation, or is it simply a way of saying that existence is eternal? This question touches on the ancient philosophical problem of infinite regress. If every effect has a cause, then we can trace causes backward indefinitely. But does that ever yield a final answer, or does it simply push the question back further and further? If universes are born inside black holes, then the process may be eternal, with no ultimate beginning. Our universe would be one link in an infinite chain. But the question remains, why is there something rather than nothing? Why do the laws of physics exist at all? Science can describe how universes evolve, but philosophy asks why there are universes to evolve in the first place. Another philosophical question is whether reality is fundamentally knowable. Our senses are limited, our horizons are bounded, and our theories are incomplete. If we live inside a black hole, then by definition there are aspects of reality we can never observe. We cannot see the parent universe. We cannot witness the process of creation. We cannot cross our horizon. Does that mean we can never know the full truth? Or can reason and inference take us further than observation? Philosophy has long wrestled with the limits of knowledge, with the distinction between appearance and reality. Black holes bring this question into the heart of science. They show us that there may be boundaries we cannot cross, not just practically, but in principle. The concept of reality itself becomes slippery. If our universe is inside a black hole, then reality is layered. There is our reality with its stars and galaxies. There is the larger reality of the parent universe. There may be still larger realities beyond that. Which of these is the true reality? Or are they all equally real, each to its own inhabitants? This touches on the philosophical debate between realism and perspectivism. Realism holds that there is a single objective reality, independent of observers, Perspectivism suggests that reality is always relative to a perspective, always shaped by where you are and how you see. From within our universe, our cosmos is reality. From outside, it is one bubble among many. Both views are valid, but they are not the same. Black holes also raise questions about identity and continuity. If a black hole gives rise to a new universe, is that universe connected to the old one, or is it completely separate? Does information about the parent universe survive in the child, or is it erased? If some trace of information persists, then universes may carry imprints of one another, like genetic inheritance. If not, then each is a fresh creation, independent and self-contained. Philosophically, this is a question about memory and identity at the largest scale. Does reality have continuity, or is it a series of disconnected moments of creation? Time, too, takes on philosophical dimensions. We experience time as flowing forward, but relativity shows that time is relative, and quantum theories suggest it may be emergent rather than fundamental. If time is emergent, then the arrow of time is not an absolute feature of reality, but a property of particular universes. Different universes may have different arrows, or none at all. What does it mean to speak of reality if time itself is not universal? Can we imagine a reality without time, or is time inseparable from existence as we know it? Another question concerns meaning. If the universe is infinite, if there are countless universes, if our cosmos is just one among many, what does that mean for the significance of our lives? Some might say it diminishes us, making us small in an endless sea. Others might say it elevates us, making us participants in a vast and ongoing process of creation. Philosophy has always grappled with the tension between insignificance and significance, between being a small part of a large whole and finding meaning in that very fact. To live in a black hole universe is to live in a cosmos that is both limited and vast, bounded by horizons yet connected to larger realities. It invites us to rethink what it means to matter. The information paradox also raises philosophical questions about determinism and free will. If information is preserved in black holes, then perhaps reality is fully deterministic with every detail encoded and conserved. If information is lost, then perhaps indeterminism is fundamental. Our choices, our actions, may be reflections of this deeper uncertainty. Physics asks whether information is conserved. Philosophy asks what that means for agency, for freedom, for responsibility. Even the concept of existence becomes complicated. In quantum mechanics, particles exist in superpositions until observed. In cosmology, universes may exist as possibilities until realized. If black holes create new universes, then existence itself may be a branching process, with countless possibilities unfolding in parallel. Does that mean that every possible universe exists somewhere? Or are only some possibilities realized? What does it mean to say that a universe exists if existence is layered and relative? For us, these questions are not just abstract. They shape how we think about ourselves, our place in the cosmos, and the meaning of knowledge. Science provides models and data, but philosophy helps us interpret what they mean. To say that we live inside a black hole is a scientific hypothesis. To ask what that means for reality is a philosophical exploration. Both are needed because reality is not just about what exists, but about what existence means. After travelling through the mysteries of black holes, horizons, singularities, entropy, quantum theories, and even the possibility of other universes beyond our own, it is natural to pause and take a breath. Because while these ideas stretch the mind, they also bring us back to something simple, the feeling of wonder. No matter how far theories extend, no matter how intricate the equations or bold the speculations, the experience of contemplating the universe is one of quiet awe. To think that we might live inside a black hole is not only a scientific hypothesis, it is also an invitation to rediscover the sense of amazement that first draws us to look at the stars. Wonder has always been at the heart of science. Long before telescopes or equations, people looked up at the night sky and asked what it was, how it came to be, and what it meant for them. They told stories about constellations, imagined gods and creatures in the stars, and used the heavens to mark time and navigate seas. These early acts of wonder were not so different from what scientists do today. The tools have changed, the language has changed, but the impulse is the same. It is the desire to understand, to connect, to find meaning in the vastness above. Black holes remind us of how limited and fragile our understanding is. They are objects predicted by mathematics before they were ever observed. They are invisible, detectable only through their effects. They bend light, distort time, and swallow matter, yet they may also create new universes. They embody the mystery of existence, the place where our theories break down and new ideas are born. To contemplate them is to acknowledge how much we do not know. And yet, in that not knowing, there is wonder. The idea that our entire universe might be inside a black hole is not meant to make us feel small or lost. It is meant to remind us that reality is always larger than we think. The horizon of a black hole is a boundary, but it is also a doorway. The singularity is a place where knowledge ends, but it may also be where new universes begin. Our cosmos, with all its stars and galaxies, may be one such universe, born from collapse in another. To live here, to think about this, is already extraordinary. Wonder also comes from realizing how connected we are to the cosmos. The atoms in our bodies were forged in stars. The time we experience is shaped by entropy and horizons. The very structure of space we inhabit may be the inside of a black hole. When we breathe, when we think, when we look at the sky, we are participating in these cosmic processes. We are not separate from the universe. We are part of it, expressions of the same laws that govern black holes and galaxies. To feel this connection is to feel wonder. It is easy, in daily life, to lose this perspective. The routines of work, the noise of the world, the immediacy of concerns can make the cosmos feel distant, abstract. But then we pause, perhaps on a quiet night, and look up. The stars remind us. The silence reminds us. The sheer vastness reminds us. We live in a universe that may be inside a black hole, part of a chain of creation beyond imagination, and yet here we are, able to notice, able to wonder. That is extraordinary. The beauty of wonder is that it does not require answers. We do not need to know for certain whether we live inside a black hole to feel awe. The possibility itself is enough. The act of considering it, of holding the thought in our minds, opens us to the vastness of reality. Wonder is not about certainty. It is about openness, about being willing to see the world as larger than ourselves. In science, wonder often leads to discovery. Questions that seem abstract or impossible can, over time, yield to insight. Black holes, once thought impossible, are now observed with telescopes and detected through gravitational waves. The cosmic microwave background, once invisible, is now mapped in detail. Ideas that begin as wonder can become knowledge. But even when they do, the wonder does not vanish. If anything, it deepens. Knowing how stars shine does not make them less beautiful. Understanding how galaxies form does not make them less majestic. Wonder and knowledge are not opposites. They are companions. In philosophy, wonder is often the beginning of wisdom. To question what reality is, what time is, what existence means, is to practice wonder. These questions may not have final answers, but they shape how we live, how we think, how we see ourselves in the cosmos. To wonder is to be humble, to recognize that reality is larger than our understanding. It is also to be bold, to reach beyond what we know. Wonder holds both humility and boldness at once. As we return to wonder, it is important to notice that we already live in its presence. Every breath, every thought, every heartbeat is improbable. The balance of forces, the fine-tuning of constants, the arrow of time. All of these make life possible, and none of them are guaranteed. To exist at all, in a universe that may be one of many, is already remarkable. We do not need to look to distant galaxies or hidden dimensions to find wonder. It is here, in the fact that we are here. The thought that our universe might be the inside of a black hole adds another layer to this wonder. It means that we are part of a process far larger than ourselves, a chain of creation that may stretch without end. It means that the horizons we see are not the limits of reality, but the edges of our perspective. It means that even in the face of limits, there is always more beyond. As we close this exploration, we do not close the mystery. Black holes will continue to challenge us, to puzzle us, to inspire us. The universe will continue to expand, carrying galaxies beyond sight. Our theories will continue to evolve, sometimes answering questions, sometimes raising new ones. The wonder will remain. Because in the end, science and philosophy are not only about explanations, they're about keeping wonder alive. So here we are, at the quiet edge of thought, looking back at what we have considered. Black holes, horizons, singularities, entropy, quantum theories, hidden dimensions, other universes, perception, philosophy. All of it brings us back to this moment of wonder, a reminder that reality is vast, that knowledge is limited, and that existence itself is a mystery worth contemplating. And in that quiet contemplation, perhaps we feel what countless others have felt when they looked at the night sky before us. A sense of awe, a sense of humility, a sense of connection. Whatever the true nature of the universe may be, whatever lies beyond our horizon, we are here, alive, aware, able to wonder. That is enough. Thank you for spending this time together, drifting through the possibilities of black holes and the idea that our entire universe might exist inside one. These thoughts are vast, but they are not heavy. They are simply invitations to let the mind wander, to settle into curiosity, and to feel how wide reality might be. If you found this gentle exploration calming, and if you'd like to join again on another journey through science and imagination, you're welcome to linger with this channel. Your presence makes these quiet explorations possible, and I'm grateful you're here. For now, let the ideas soften into the background. Let the rhythms of thought fade into stillness. The universe is wide, horizons stretch beyond sight, but here and now you are safe, you are steady, and you can rest. Good night.